School of Civil Engineering, and I would like you to welcome to the UPV, welcome to our campus, to our school, and of course, welcome to this workshop organized by the Endure Project, as you already know, Consolidator Grant, financed by the European Research Council. And my only task today here is welcome you to our campus, to the university, to say hello, good morning, and to thank Professor Jose Miguel Adam and all his team, because I think they are doing a very great job. And this job also serves the purpose that our university is right now one of the top universities around the world in structural and construction engineering. So many thanks, and many thanks all of you for coming here. Also, I hope you enjoy the workshop, our campus and the city, and that's it. For sure that you are not going to listen to me, but to listen to the very, very good lecturers that Professor Adam has brought to the workshop. So have a nice workshop, and I hope you to talk to you later in the coffee break too. Okay, thank you.
So thank you very much.
Your turn?
It's my turn, yeah. So thank you very much, Professor Pellicer. So it's time to start the technical part of the workshop. So yeah, as you know, we have six presentation, very interesting presentation on preventing building collapses. The first one, Andri Setiawan, is a doctor at the UPV. Second one, Mark Stewart from the University of Technology Sydney in Australia. The third, Sarah Orton from the University of Missouri. Well, we'll have a break at 10:40, and next talk with Renata Obiala from ArcelorMittal, and we'll next Miguel Fernádez from UPM Madrid, and we'll finish with Nirvan Makoond, a postdoctoral researcher here at the UPV. So I feel that we can start with the first presentation. Andri Setiawan, are you ready for a presentation? So Andri is a postdoctoral researcher here at the UPV, working on structural robustness. He's our expert on concrete structures. And the title of his presentation is An Overview of Endure. Endure is a project funded by the European Research Council with 2.5 million euros. And we want to avoid failure propagation in building structures. So Andri, the floor is yours.
Okay. Okay. So, good morning, ladies and gentlemen. First of all, thank you very much for attending our workshop today. My name is Andri Setiawan, and this morning I'm going to give an overview of our Endure project. But before I start, there are two things that I want to say. The first one is all the materials that will be presented today were like curated, designed, and produced by the whole team. So credits to the whole Endure team. And the second thing is, since I'm the first presenter today, I'm going to spend some of the few minutes of my presentation to introduce you to the context of why this workshop is important, why building collapsing, and what can contribute to building collapse, and what are the current best practices that we have and what we want to improve in Endure. So I'm going to start now. Unfortunately, our world is at risk. According to the Global Risk Report that has just been released this year by the World Economic Forum, they interviewed 1,500 global leaders across many different disciplines from government, economic, educational institution, and they asked, can you identify 5 global risks that we are currently facing in 2024? And here I show you some of the examples, and the percentage here indicates the share of respondents. And we can see in the number one, 66% of the respondents agree that extreme weather is our main problems. Also some other global risks, and I want to highlight another two, which is related to the escalation or outbreak of interstate armed conflict followed by attacks on critical infrastructure. So I'm going to spend a few minutes showing you some statistics, some interesting numbers about these risk in particular. So let's talk about the extreme weather events. According to the human cause of disasters, the number of reported disasters in the last 2 decades has risen significantly in terms of number and also consequences in terms of human lives and also economic losses. But one thing that I want to emphasize here is we can see very interesting chart here that these extreme events doesn't, let's say, leads to the same consequences all around the world. But for example, if we see the total deaths per million inhabitants shown by the black bubbles here, we can see that most of them are located in sub-Saharan Africa countries and Southeast Asian countries. So what I want to highlight here is when we speak about threat or hazards, it's just one side of the coin. But the other side of the coin that we usually overlook is vulnerability. And this is mostly something that we can do about as engineers and researchers. So I usually don't really, let's say, into like media or news because sometimes they are misleading, sometimes they are a bit biased. But I want to show you two headlines that I think I'm fully agree with. This one is from Huffington Post that was written in 2016. It says that natural disaster cause way more deaths in poor countries than rich ones. So this also indicates that vulnerabilities plays a crucial role. And the second one, this is also very interesting from NBC News about the world's most earthquake vulnerable cities. I'm going to read the headline. When it comes to earthquakes, a magnitude 6 rumble in San Francisco may feel and shake the same as 6 in Bali, but you are far more likely to die in India. So once again, I want to highlight that there are two sides of this problem when we talk about risk, and we want to focus on the vulnerabilities of our infrastructures. So now let's move on to the second, let's say, risk that we are encountering related to political polarization that leads to interstate armed conflict. There are some photos from the damaged building in Ukraine and also some buildings in Syria. And this is the chart that I found interesting from the Global Risk Report. You can see that the total armed conflicts here from 2010 to now, I think it's almost doubled. And worstly, in terms of fatalities, we've seen some peaceful time here, but then it almost quadrupled here. So we are in the turmoil situation. And once again, we can see that most of these wars are not uniformly around the world. It also happens mostly in Africa, Asia, and Middle East. So once again, the situation will be worsened by the quality control of the infrastructures that we have, the disaster mitigation that is lacking in these regions compared to, for example, in Europe and or America. In addition to these two, let's say, hazard that is tangible that we can see, our buildings is also subjected to aging infrastructure. For example, this one is the statistic that is quite surprising also. Share of percentage of buildings built before 1980 in Europe. And you can see, I want you to focus on this black colored map here, which indicates that more than 70% of the buildings in these countries are built before 1980. So we are almost reaching the end of the service life of all buildings in Europe. And there are many issues with aging infrastructures that may lead to building collapse as well, like including reinforcement corrosion and also like cracking and spalling of concrete that we need to also take into account in our problem. So now I'm going to move on to speak in more technical about building collapses, some events that happened in the past and what we can learn from them. Starting from Ronan Point apartment, I think this is the most, let's say, important event in robustness design happening in 1968 in the UK. There was like a blast happening in the 18th floor of the buildings that caused the partial collapse of the whole corner bay of this apartment building. And this was the first event that triggers the development of official, let's say, first formulation of robustness building codes. And then followed by another big incidents, unfortunately, in Seoul, the Sampung department store that was collapsing and causing more than 500 casualties and injuring more than 1,000 people. And until today, Sampung department store is still the deadliest non-related war disaster in South Korea, and also the second one in the world after Rana Plaza collapse. And there are many causes of leading to this collapse, including change of use of the building from ice skating rink to restaurant, and also changing or design error, reducing column size, and so on. So all of this combination leads to the catastrophic collapse of the sampling department store. In the same year, there was Oklahoma bombing in Alfred Murrah Federal Building, where there's like a truck with more or less equivalent to 2,000 kilogram of TNT explodes 5 meters away from the building, blew away the whole facade in one side of the building, like 1/3 of the building actually. And this also how the federal building in the US designed since this incident. And lastly, the one that happens not so far from now, which was the Templin Tower South. And until now, they are still doing the investigation to find out the root cause of this incident. But there are many indications stating that there are a combination of deterioration and also aging of the structure. So after seeing this collapse, we are going to discuss in more detail about what happened to this building. And I think the best way to do it is to describe what is progressive collapse. There are many different definitions of progressive collapse, but I'm selecting one today, which is from the GSA. It says that progressive collapse is a situation where a local failure of a primary component leads to the collapse of adjoining members, which in turn leads to more collapse. And then the total damage is disproportionate when compared to the origin. There are three keywords that I want to highlight, which I think emphasize what is progressive collapse. First is most progressive collapse happens due to local failure. So this local failure can be triggered by many different things, can be explosion, can be fire, or can be also vehicle collision. And this local failure leads to the propagation of additional collapse in the surrounding system, leading to what we usually call as like a chain reaction or like a domino effect. And the resulting collapse is disproportionate when compared to its origin. So this is the video that our team creates to demonstrate what is progressive collapse. So this can be like a load in the building, and when we remove like one structural local failure in the building, it then propagates to the rest of the system. This one is partial collapse, but this can be worse even to propagate to the rest of the system. So what is the philosophy that engineers adopt to design with progressive collapse? I'm not going to go into much detail about this probability theory. Probably Mark will discuss in more detail after me. But I'm just going to show this expression because it elegantly expresses the philosophy that engineers adopt to deal with progressive collapse. I'm going to start with the hazard. So total probability collapse consists of three components. It starts with the annual mean rate of occurrence of hazard H. And what can we do in general to deal with this hazard? Mostly what we can do is trying to, let's say, change the layout of the building in order to make sure that we have substantial like hazardous substances in the building. We need to store it, let's say, far away from the crowd, and also educating, let's say, building owners if we have something in the building that might be hazardous. And the second component is if this hazard cannot be prevented, and if this hazard already happens, this hazard can cause local initial damage. So as engineers, we need to also minimize probability of having this hazard to cause local initial damage. And this can be prevented, for example, by designing key elements, introducing additional element like, for example, FRP or jacketing in the pier of the bridge, or creating like, for example, like a barrier in bridge crossing the river to prevent vessel collision. But then, if this local damage happens, let's say if we cannot prevent this local damage, then we move on to the last component, which is the propagation of collapse. So probability of having this proportional collapse given the local damage happen. So this, we mostly rely on the redistribution of the system, how different alternative load path can be developed in order to redistribute the loads from the failed components to the surrounding system so that we can achieve a new equilibrium without having partial collapse. So this philosophy is applied to building codes. And how we apply this? Let's see first by the evolution of codes. The first, let's say, official codes of practice was written in 1972, just 4 years after the Ronan Point collapse. And this code has been, let's say, developed, adopted, and modified to many different codes all around the world, Eurocode and GSA and UFC in the US, and also the most recent one from ASCE 76. And we are also expecting the second generation of Eurocodes. I think it will be published in 2025. If we extract, let's say, the main essence of all these codes on how to deal with design for robustness, we have three main approaches. First is the key elements. This one deals with prevention or minimizing the local damage. So we can have a column that is like bigger or stronger, or putting FRP or jacketing, basically to make sure that if some hazard happen, our main critical components, mainly the vertical load-bearing elements, can still survive this hazard. And the two, which are focusing more on the continuity and ensuring that if local failure happens, we can have sufficient distribution capacity in our system. So this morning, I'm going to focus on the last two, which I think will be, let's say, strongly relevant to endure. First, I'm going to highlight when continuity is effective, because in most cases, they are also effective, but also in the other extreme, when continuity can actually backfire or it doesn't work effectively. So let's start to discuss when continuity is effective. So our group has done several full-scale tests in the past, investigating flash slab structures here and also precast structures. And if you can see here in the video, we are removing the corner column from the building. And thanks to the continuity that introduced to the whole system, you will see here, there is like an impact, a deflection in the building, but the structure survived with very minimum damage. And also in the structures, we cannot even see like almost like a vibration here. So in this scenario where you have like a local failure that is mostly concentrated in one particular part, and let's say the size is relatively small, then continuity is of course very effective, because this helps to distribute the loads from these failed components to the surrounding column through the beam and slab system. So the continuity here playing a pivotal role. But then when continuity can actually backfire. So there are some scenarios that can show when continuity can backfire. The first one is if you have like a local foundation settlement, for example, if you have an elongated building and then there is like a significant settlement only in like one small area in the building, continuity can actually pull the rest of the system that was previously unaffected. Or if we have a wide span structures, a long span structures, mostly consisting of like precast system or post-tension slab system. For example, we are modeling here like a building with 10-meter span, and the removal of a single penultimate internal column here, probably you can see that it's in the ground floor here, the penultimate internal. A loss of single column in this region, in this bay, actually pulls the rest of the system to collapse. And lastly, what happens if the initial failure is not small? Because in reality, we cannot control whether the building can only be damaged by one column. For example, if you have a collision or blast that spread in several columns in the building, for example, this is like a hypothetical scenario where we remove fully one segment, one internal segment of the building. And you can see in the animation that I'm going to show you next that this actually pulls the whole building. So the loss of one segment because of continuity pulling the whole system to collapse. So, of course, here continuity can be effective in many cases, but it can be improved for this, let's say, three scenarios. Of course, there are many other scenarios, but what I want to highlight is there is a potential for improvement for continuity. So let's try to, we don't need to really like reinvent the wheel, but what we can do is start by revisiting the past. Revisiting the past to invent the new. So the other extreme of continuity is segmentation. So having buildings that are compartmentalized without having continuity. And in some cases, this can actually help to isolate collapse. So for example, the photo here shows the partial collapse of Terminal 2E in Charles de Gaulle Airport in France. And due to the structural segmentation or structural joint between this terminal to the other parts of the building, the collapse of Terminal E was like completely stopped in this particular segment, structural joint, and it didn't spread to the other parts. Another very interesting example was the Pentagon attack in 2001, where there was like a plane crashing to like one side of the perimeter side of the Pentagon. And we can see here on the left side of this crash, you can see like a very thin cut because of the structural joint here. There are two lines of columns here located in this particular part of the building. Whereas on the other side, we have what we call like a strong border, basically consisting of columns with a very like densely spaced spiral, like the one that we use typically in like seismic design. And this spiral helps to maintain the integrity of the core of the column so that it can still withstand this impact and redistribute the load. So of course, having segmentation alone can be also tricky to design due to like durability issues and also sensitivity to like a local failures. So what we are trying to do in Endure is to try inventing a new philosophy where we combine the positive or the advantages of these two main extremes, combining segmentation and combining continuity. So I'm going to show you a video about the lizard. I hope there was no lizard hurt during the process, but you can see here that when there is like a predator lizard shed its tail. So why it's relevant? Because the way we design or the way we approach views-based segmentation, combining continuity and segmentation, is actually very similar to the way lizard escape predators. So there was like a recently very interesting study written in Science by Baban et al. They tried to do like a microscopic scan of the lizard tail, and instead of having like a single monolithic unit that we probably think, the lizard tail actually composed of segmented fracture planes that are designed to break, deliberately designed to break. So our views-based segmentation that we will apply in our buildings will adopt more or less, let's say, similar concept. We will have continuity. We will have the tail when there is no predators, when there is no threat, and this will help to, of course, ensuring that the building can function properly during service. And also, if you have small initial failure, we have continuity to deal with the distribution. But then, if there is a failure that is too large to withstand or too large to contain through continuity, it will segment. So it will isolate the collapse so that the collapse will not spread to the rest of the system. So with this, we have what is called fuse-based segmentation, or you can also call it like scenario-based segmentation. So we only form segmentation when it's needed. And how we implement this philosophy, because probably this is a bit like abstract, but how we implement this philosophy in building design. There are two ways to achieve this philosophy: strong borders and force limiting elements. Strong border is probably the most straightforward one. We have seen how it works perfectly during the Pentagon attack. So basically, you can see the illustration here. When the collapse front propagates, we have strong elements indicated by this red block that basically withstand the collapse front so that it will not propagate to the rest of the system. And how we do this in real building? This can be done by even like conventional column that we design, for example, with a seismic requirement like spatial moment frame, for example, with ductility class high. Or we can also take advantages of core wall or shear wall that we have in our system. Instead of just having these walls to resist wind or earthquake, we can also position the wall in order to segment the building if it's needed. Another thing that we can impose if we cannot have strong border is the second approach where we have force limiting elements. So this is a very nice illustration. You have the chain reaction here. Please focus on the red highlight part. And you can see when there is a pull, these elements tend to break, like a fuse in electric component, for example. So these force limiting elements, basically the idea is to limit the transfer of force from the collapse front to the rest of the system so that it will not propagate. So there are several, let's say, methods that has been actually used for seismic, but also we found it to work relatively well for collapse. For example, in steel construction, we have what is called like dog bond or reduced beam section, where we basically cut the flange so that we don't transfer high moment to column. And this actually also helps during collapse because the column will survive better if there is no significant transfer of forces from the beam. Or in the concrete structures, it's a bit more difficult to achieve, but we can have what is called like a plastic hinge relocation, having a special detail. For example, this one protect the joint from like strain penetration happening on the plastic hinge. So Endure aims to develop these ideas so that it can be applied in real buildings to prevent collapse. So it has started since 2022, and now we are exactly in the halfway of the project, and we still have 2.5 years more, and hopefully we can achieve what we aim at the end of this project. But today I'm going to give you a brief overview of the methodology of the structure of Endure and what we have done so far until today, and also explaining what we will try to do next. So Endure composed of 3 main work packages. Work package 1 mostly deal with the performance-based approach to design few segmented buildings. So work package 1 focusing mostly on the framework on how we need to identify what buildings need segmentation and how we should segment the building. Work package 2 deals more specifically about the design of the structural views itself, for example, the force limiting elements, but also the design of the strong borders. What are the requirements? What are the details that we need to create strong borders? And also implementing this concept, the strong border concept and the force limiting element concept to a subassembly, basically like a scaled down part building that we extracted, and we subject this building to like a collapse scenario, and we evaluate whether the fuse or the strong border can actually prevent the collapse of the rest of the system. And lastly, in work package 3, we are going to extrapolate understanding that we have obtained in work package 1 and 2 to test the concept in full scale buildings. I think work package 3 will be very important in our field where the industry is a bit inert and a bit, let's say, skeptical with new technologies. So the success of work package 3 in validating the concept in full scale building will be very useful to convince stakeholders and building end users. So work package 1 starts with collecting the database of real collapses. In work package 1, it's a bit cut here, but there are actually 40 cases that we gathered from all past collapse events all around the world. And based on these 40 collapses, we classify what are the main hazards causing collapse, and then where the initial failure is, spatially in the building, and also what components are the first that are triggered by this hazard. For example, how many are triggered by columns, beams, joints, slab, wall, and their structural components. So as we expected, mostly are triggered by column, which is the critical vertical bearing elements. And then we also try to classify the type of propagation, whether it's type collapse or whether it's domino collapse or pancake, like almost like two vertical collapse. And then we quantify or we extract the record about the consequences that are related to each of these incidents. From this analysis of real collapse, we try to develop several, let's say, hypothetical building design, taking understanding of when actually continuity can backfire, and then we try to investigate in more detail with different buildings configuration, different building spans, different building heights, and investigating these buildings with different initial damage scenario to investigate when continuity can be ineffective. Because when continuity is ineffective, it means that the building needs to be cemented. So based on the analysis, we do the fuse-based segmentation configuration. Basically, we deal with the framework. The first question, of course, that we ask in the design is whether this building needs segmentation or not. Whether the building can be benefited from having segmentation. And if the answer is yes, then there are more framework that we need to, let's say, incorporate in the design process to determine where and when, how we should segment the building, what would be the ideal or optimum segment size in order to contain the collapse effectively. And the last step in work package 1, based on this framework, we will try to demonstrate the benefits of having segmentation when compared to building without segmentation. Of course, we have different collapse area for the same initial failure, for example, here, and then we can quantify the consequences of these two scenarios so that we can convince, once again, stakeholders, building owners, and end users that having the segmentation can save lives and save monetary values as well of the properties. And then in work package 2, there are two main activities that now we are currently working on. The first one is designing the force limiting elements and doing some prototype testing to see how reliable they are and whether they can be manufactured precisely. And to do this, we will try not to reinvent the wheel. We will try to adopt what we have so far in the industry and then make some adjustment and modification. So in order to do that, we develop a multi-criteria analysis with these 9 parameters with different aspects that we consider. For example, the reliability of the fuse, how durable is the structural fuse, and how compliant is this fuse to other load paths in the building, and so on. And using this criteria, our team evaluated 26 potential fuse designed for reinforced concrete structures and another 22 for steel structures. These are just some examples that we gathered from the literature. We can have some precast connection system, or we have like mechanical coupler, or we can have like a pin connection system that is quite common in the steel construction, and also some additional corrugated plate or reduced beam section, for example. And for the reinforced concrete structures, according to this multi-criteria analysis that we perform, we evaluated mechanical coupler as the most, let's say, practical solution that we can achieve. But the interesting thing here is we want to do the opposite of what traditional coupler does. Because traditional coupler is always designed to be stronger than the two bars that are connected to it. But since we want to have this mechanical coupler to behave like a fuse, we need to design this coupler to be weaker, but not too weak so that it breaks under small failure, but not too strong so that it will propagate the collapse. So there is like a window or a gap that we need to design this coupler to have a specific threshold of force so that it will be triggered when needed. So we try to do different modification, introducing, for example, here like windows to reduce the cross-sectional area of the coupler. And this one we introduce like grooves, like a cut, so that we can, let's say, achieve the depth or the cross-section area that we want, or simply shortening the coupler so that we can have less engagement between the ribs. And we have done more or less 30 tests on these mechanical couplers, and we are quite happy, let's say, with the results. These are reliable in terms of we can design and predict accurately the level of forces that these couplers can achieve before breaking. And all of these couplers always fail in the coupler itself, not in the bars. So this achieves the function of the fuse. And then, in addition to this, we also work with different strong border design, although we don't do the laboratory testing for the strong border design. But we are trying to adopt several, let's say, design strategies, different detailing, mostly coming from quick engineering. For example, special frame. We found that with the special frame, let's say, requirement, this works relatively well for building. So we are trying to adopt this kind of detailing and also other criteria. After doing this prototype testing, we are not yet there, but we are planning to perform a sub-assembly design. So basically, this is the building that I showed you earlier where the internal segment was removed and it's completely collapsed. So now our objective is we need to stop the collapse of this building to happen. So to do that, we extract one particular, let's say, section of the building located in the ground floor, and we model it in the lab. We call it like a sub-assembly specimen. The subassembly represents more or less parts where the collapse will coming. So the collapse will come from the right side of this part. We model the pulling force and the collapse force using these two hydraulic jacks. And then we have more or less the reaction frames, and part of the slab and beam here represents more or less the intact structures that we want to protect behind our border. And we are going to test 4 specimens, 2 for concrete, 2 for steel. And for each structural system, for example, in concrete, we will test strong border alone, let's say, without introducing any structural fuse. And in the second test, we are going to try to combine the two. So having strong border and also force limiting elements in order to compare whether we can further improve the performance or whether there is no significant improvement that we can achieve. So we don't know yet, but we are going to test it in the coming months. So in work package 3, I'm going to be very short here because my colleague Nirvan this afternoon will describe in more detail about the test that we did in work package 3. Basically, we have done the full-scale testing of the precast building specimen. This building was like, let's say, heavily instrumented with more than 50 sensors, I think almost 100 sensors with different strain gauges located all around the system with LVDT and accelerometer. And we are trying to incorporate the, let's say, philosophy in this building by adopting partial strength connection of the precast system and also combining it with like a stronger column in order to prevent propagation of collapse. And in the future, we are going to test more or less similar scale buildings, two buildings, one cast in situ concrete and the other one is still buildings. So the idea is more or less to have the same gross floor area, more or less having the same geometry and topology with the cast building that we have, so that we can make like a systematic comparison between these three buildings. And yeah, we will try to introduce like activity class law in the original design of the building. But of course, if we end up with a strong border, we might need to do some modification on this. So since the project is not yet finished, I will not make any conclusion or any statements or anything to claim about the project. I'm going to highlight about, let's say, the impacts that Endure can bring from its success. Scientifically, the success of Endure will open a new paradigm for next-gen robustness design. By no means to eliminate or substitute what has been done and what have been working in the past, for example, continuity, but the goal is to complement it, to provide the last line of defense in the building if other measures fail to do so. Socially, this is the biggest goal, and our project is to create more resilient society, more resilient buildings, and to save lives from future collapse. And environmentally, with more robust buildings, we can also expect longer service life so that we can also help to reduce carbon footprint, which is a big issue in our planet Earth. So I'm going back to the first message that I was telling you. Our world is at risk. This is probably inevitable, but we can create a resilient society so that hazard doesn't really mean to be translated to be disasters. So thank you very much for your attention, and I hope you enjoy the rest of the workshop. Thank you.
Andri, thank you very much for your very interesting presentation. I think that we have time for a couple of questions. So, any questions from the audience regarding the project? Yeah, unfortunately, I don't have questions because I know very well the project. So, no questions. So we can move on to the next presentation. Andri, thank you very much.
Thank you.
Well, so now we have a new talk by Professor Mark Stewart. Mark Stewart is a distinguished professor of civil engineering and director of the Center for Built Infrastructure Resilience at the University Technology Sydney. So, Mark, the floor is yours. Ready for the presentation? Yep. And thank you very much for coming to Valencia. 42 hours traveling by plane. Yeah. So, truly appreciate your visit.
Okay, well, I really have to thank Jose for getting me involved in this very fascinating project. And we just heard from Andri, about the scope and how innovative I think this is. I also have to thank Jose and his team for being such gracious hosts while I'm here as well. So you've really shown me some good parts of Valencia. I'm looking forward to seeing some more parts. I'm really enjoying my time here. So thanks, Jose. How do I move? Okay, so Andri actually, gave a pretty good introduction to risk, and risk assessment, which is really my interest. And the last 20 years or so, I've been very interested in explosive blast loading and terrorism. But what I want to talk today is about this, but the principles and the methods and the philosophy can be equally applied to seismic actions in terms of progressive collapse or to other types of abnormal loading. That's it. Okay, so the motivation for me is about risk, and obviously as engineers we like to think about numbers rather than just adjectives. So risk occurs in the spectrum between full certainty and complete uncertainty. And so risk lies somewhere in the middle. And it's really about the likelihood of the hazard or the threat as a product of the vulnerability of the infrastructure we're looking at, and then the consequences, in terms of lives lost or economic losses or other social or indirect losses on top of that. And I suppose that the key thing about this is risk provides as a good framework to quantify the benefits predictive measure. So if you want to invest in having an enhanced structural design, that comes at a cost. But what's the benefit? How much does it reduce the risk? How much does it reduce the risk of loss of life or the risk of damage or sort of other consequences? And then the key question is, are the gains in safety worth the cost? So it's really like a cost benefit analysis. We're trying to find that sweet spot where the benefits exceed the cost. And then that provides some evidence-based or really performance-based that we can then go ahead and implement. We believe is going to be a cost-effective safety measure. So just a bit of background to some of the work I do at UTS in Sydney. We do a fair bit of defence security work, and it's really about what's the reliability of the loadings and in terms of logistics. So that's really about what's the probability model we have that we need. How vulnerable will infrastructure be to those particular hazards? What's the risk of damage and casualties, which I'll talk about today. And the main thing is really how can we make rational decisions? So it's just really about rational decision making, recognizing that there's a balance between the risk and the cost. So my background is publishing risk assessment for those who don't know me, and Rob Milters and I wrote this book in 1997. And what's interesting is that the philosophy of public risk assessment can apply to all sorts of systems. Right? It's not just structures, it's not just blast. So these are some of the things we've worked on. Looked at buildings and bridges and pipes and LPG and nuclear facilities. We've looked at natural hazards, wind, seismic, climate change. We've looked at corrosion. We've looked at human factors. We've looked at blast. There's a whole lot of infrastructure systems and hazards that we can model all within this framework. And our book was translated into Japanese about 10 years ago and Chinese about 2 years ago. So a lot of this is still current. And it's really about low probability, high consequence events. So it's really extreme events, right? And that's where decision making is really difficult to tease out. Just what's the best thing to do? We published a few books on counterterrorism. This is the first book published in 2011 with my colleague Jim Mueller in the US. We've extended that. We've started to look at the cost-benefit analysis of counterterrorism policing in terms of the FBI, the federal police, other agencies around the world. We then looked at aviation security at airports and aircraft, or thinking about terrorism. We done a lot of work on climate adaptation engineering, so I'm quite interested in climate change and just engineering to extremes. So there's a whole range of applications for risk assessment. So we'll talk about terrorism, and most you know what's going on. I'm really interested in some improvised explosive devices that they can be homemade, at least in Western countries. We're lucky that most of the attacks in the West are lone wolves or self-starters, so most of them don't actually succeed. It's quite rare to have a successful car bomb or IED attack in the West. And I've been mainly focused on vehicle attacks because several tons of explosives, and that's what's going to really damage buildings and other infrastructure. But there's other threats. This is what we call the Skippy bomb, and it was again, some of these guys come up with the weirdest plots. This is a teenager in Australia in 2016 came up with a idea in Sydney, mind you, to get a kangaroo, paint it black in ISIS colours, put explosives onto it, and let it loose in downtown Sydney. I mean, completely fanciful. But this guy got sentenced to, I think 10 years jail. Right. So when you're talking about terrorism, there's so many different types of threats. So if we start thinking about structural reliability, we're trying to work out the probability of failure. And the key thing here is that we are interested in, so get this right. Yeah, we're interested in really what's the variability of our loading, what's the variability of our resistance, and then we're trying to calculate the probability of failure is when our load exceeds our resistance. So we're really worried about this, that the upper tail of load effects and the lower tail of the resistance. And in most cases, in terms of performance-based design, this probability of failure in building standards is about 10 to the -5, maybe 10 to the -6. So we're looking at very extreme unlikelihood. The key thing is we want to think about what's the variability, what's the uncertainty, what's our confidence that we know what the loading is going to be. And often this loading represents the peak load in 50 years or maybe 100 years. And then we're trying to think about what's our, how certain are we about the concrete strength or the variability of the yield strength or the dimensions. And this is a basic framework developed in the 60s, and it applies to really every hazard you can think of and every type of structural system you can think of. So I'm interested in terrorism blast, and this is a picture from an attack at the Australian Embassy in Jakarta in 2002. The embassy had recently been hardened, so the embassy did quite well. But you did see all the damage to the adjacent civilian infrastructure, which wasn't hardened. Right, extensive glazing damage. And what we really focus on, we want to focus on the loading side, the air blast variability, and also on the structural response side. So you need to look at both sides of the equation here. So in terms of air blast variability, what we've done is, in conjunction with the Royal Australian Air Force, with the Australian Defence Force, we're able to do a lot of blast testing, maybe 1 to 2 kilograms. And what we're trying to do is we have an explosive here. We have these pressure gauges, 8 pressure gauges, exactly the same. And we're trying to measure, well, what variability do we see at each of those gauges? Now, theoretically, you should get exactly the same pressure at every gauge. But we don't, right? We see that there's some variability. And so we did more than 90 tests over several years. And that's sort of what we get. It's fairly small scale within a bunker. And this is the time pressure history. So this is the pressure over time. And from I think 4 gauges, and we're seeing plus or minus 10% difference in the peak pressure there. So we're seeing variability. Right? And that's what I like to see. I like to see that. And then we start thinking about, well, if we compare the test result to the model that's used to predict the blast pressure, then we work out, well, what's the error between the model and the test result gives. So obviously, if it's 1, that means it's perfect, and the average result is about 1, which is pretty good. But there's a pretty large scale, plus or minus. This like some pressure values are 40% higher, some are 30% lower. So we want to consider that in terms of, in this case, log normal distributions. And triggers for collapse. I already talked about the innovation for that. I don't need to talk too much about that. And what we're trying to, so this is a sort of illustrative example. It's a little bit realistic, but not that realistic in the sense that it's just something we can do in like 6 months. But we said, okay, let's look at reinforced concrete building. Let's assume a 10 stories high. Let's say the footprint is really just 5 columns across. Right? We're only considering the actual load of the column as the main failing mechanism. Right? We haven't modeled this as a structural system. We just really just modeled this as a column. Right? And there's a load on it. So resistance is really just the standard equation we get for columns. We said, well, let's assume there's a car bomb, a vehicle-borne improvised device. Let's say it's 10 meters away from the middle column. and let's say it's 1,000 kilograms of explosives. Right? So it's just a scenario to go through and illustrate some of the concepts. We use a Daniel system, which is a structural reliability analysis, which really takes into account the fact that if you lose one element, the load gets redistributed to the adjacent elements. Right, so we have this load redistribution from the damaged columns. As you saw in Andre's talk, that if you lose one column, you're not really going to get progressive collapse. We assumed, for sake of illustration, that's just if two columns are lost and the adjacent columns, then we assume that therefore causes progressive collapse. Right? It's just an assumption to help keep the model working. Right, and there's uncertainties, right? So you might have 1,000 kilograms of ANFO as ammonium nitrate fuel oil, which can be homemade, right, and mixed. Let's assume it's 1,000 kilograms. Let's assume that when the terrorists make it, they might aim for 1,000 kilograms, but it might actually be a bit less. It might be 950 or maybe 1,050. So there's some variability in that. We call that the coefficient of variation, which is the standard deviation divided by the mean. So that uncertainty is quite narrow. Bigger uncertainty is how the hell you mix it. Right? ANFO has to be mixed really carefully to get the full energetic property. So if it's mixed perfectly, it's going to be equivalent of about 0.8 compared to TNT. So have 80% of the charge or the effect of TNT. So TNT is always seen as a reference here. But if it's made poorly, it can have 0 TNT. It's just a dud. It's just a fizzer. Right? One example was the so-called Times Square bomb. Right? There's an ANFO in the back of an SUV parked in Times Square. When they found it, it looked a little bit like this, but not fully like this. But when the security services analysed what it was made up and everything else, they worked out that if the perpetrator had tried to detonate it, there would have been 0 explosion. Right? They actually used homemade. They actually used fertilizer, right, which has 0 energetic properties. So they didn't even have the mixed ones. So in this case, we assume, well, actually, if they're competent, it's going to be really effective. If it's going to be 0, and so we assumed it's going to be just between 0 and and 0.8. That's just assumption. I've done a lot more work thinking about how that can be, but I can't publish that. Well, I can. Well, no, I can't tell you guys essentially. And then the range, right? So we might think it'd be 10 meters, but it depends exactly where they park the vehicle, and they can't park it exactly where they want to park it. So we assume that it's located plus or minus, 2 meters. So we get a standard deviation of 1 meter in one direction and 1.5 meter in another direction. So there's slight variability in each of those. Then there's a whole lot of statistical parameters. There's this variability of the blast load, the variability of the loading. So there's the dead load, which is normally about equal to the design load. But the live load, the arbitrary point in time live load, is going to be quite low. It's 0.17 of the design load. So in Australia, the design load Q is 3 kPa. So this is something. So the actual live load at any point in time in a building is probably going to be about 0.5 to 1 kPa. Right? The design load is based on a load you get once in 1,000 years. Right? So it's not going to happen at the exact time of a blast, or in an earthquake, or any other abnormal loading. And then there's variability of the column in terms of the reinforcement ratio, the compressive strength, and in most cases the mean values are higher than the design values. Right, so the design values are normally picked at a lower 5th percentile. The mean value obviously is going to be higher. So that gives you some extra reserve capacity, and that's why our structures are relatively robust, because the actual capacity is normally significantly higher than what the design equation, or what the design code says, because we want to err on the conservative side. Right, when we run our Monte Carlo analysis through, what we find in terms of blast load, and this is the peak effective pressure, US guidelines and what is used around the world, the UFC tell us the load design value would be like 3,000 kPa. But because the vehicle might be a bit closer than we think it is, the variability of loading could be a bit higher one way than the other. There's a reasonable chance that the actual pressure on the building could be double what the design value is. Right? So this is a case where the design values for loadings for blast tend to be not conservative, right? Because they're really scenario based. For natural hazards, live loads, or wind and seismic and snow and wind and everything else, the design code loads are normally conservative. But the main thing here is that there's a large variability in our loading side of the problem, as well as on the resistance side. When we do Monte Carlo analysis, we look at what's the pressure on the building and the impulse, and this DI represents a damage index. Damage index of 0.8 means that you've lost 80% of the capacity of the column due to blast. And so this is really, this rating here is failure. Down here, the blast has only lost less than 20% of the damage, so it's normally going to be quite safe here. Right, so we're really looking at the unlikely event that we get a much larger blast effect than what we think we would based upon the design standards. And so we then looked at, there's several ways to blast resistant a design. One is you can minimize it by what we call the threat dependent design, where you basically strengthen that column or the columns to resist the blast scenario that you're expecting. So, and that's based on UFC 33402, and that's based on a limit state. So you basically design that particular structural member for that particular blast, so that the column is going to be much larger than the conventional building. Or we have the alternate load path method, where the building has to be stable even if you remove a single column. But in both these cases, you end up with larger member sizes, and obviously high cost. So conventional design, in this case, it might be a 500 square column. The threat defend design will be 675. Alternate path method, maybe 600. But you're actually making the building large in terms of structural elements will be larger, and so there's going to be a cost there. The collapse probability given the attack, conventional design will be about 22%. Right? So if it happens, there's a pretty good chance that you will get percussive collapse, a 1 in 5 chance. If you design for it to be blast resistant, then the probabilities become very, very low. Right? Which is what you would hope to see. So the risk reduction is greater than 99%. So blast resistant design is very effective. Right? You're getting nearly 100% reduction in risk. Right? But there's a cost because you need to have much larger structural members. So, and in most cases you think, well, these numbers, they're pretty low. Right? This is assuming that you do have an attack, and the attack itself is going to be relatively unlikely. So then the question is, well, these numbers are great. What can they tell us? How do we balance risk versus the cost? And the key question is, what's the likelihood of a terrorist attack occurring on that particular building? And the key question is, are these risks acceptable? Right? Are these something that we can live with, or are they things we need to actually mitigate what those risks are going to be? So the question is, how safe are we? Right? And so this is a fairly great, simple approach, but it just illustrates the point. We can assume that the probability of the hazard, the probability that there's a successful attack might be 1 by 10 to the -4, right? And that's per building per year, right? So you might think there could be an attack somewhere in your country, but to think about that, but to think about exactly which building that is going to be becomes a very low number because there's so many targets. So it depends on what threat advice you are receiving. Right, and so we take our hazard probability times the probability collapse given, which is what we looked at before, was 22%. So the probability of failure annually is about 2.2 by 10 to the minus 5. So we're getting pretty low numbers. The ISO standard on general principles of reliability of structures would tell us that the acceptable probability of failure is lower, 1.3 by 10 to the minus 3, based on the consequence class and the cost of life-saving measures. And so in this example, you say, well, actually, the conventional design is unsafe. The probability of failure is pretty low, but it doesn't meet the target reliability. Right? And that's the basis for performance-based design, is to make sure a reliability matches a target or is actually exceeds our target. But obviously, you can do a lot more detail in the analysis. But it just shows the information we need to work out are the risks acceptable and how safe are we. And so if you want to, you can then go on and do a cost benefit analysis, because at the end of the day, most decisions are made by either government or they're made by owners of infrastructure, and cost is really important to them, right? So they need to see that what they're doing is cost effective. So what we have a threat or hazard, we have some protective measure, right? And it could be like a segmentation fuse, for example. And we hope that would reduce the vulnerability. It might enhance the resilience. It might reduce the exposure. And therefore it might reduce the consequences. And so all of those together is going to give us a reduction in risk. So hopefully we'll get, like we saw in the example before, we'll get close to 99%. And so that reduction in risk gives us our benefit. Let's say we reduce the risk by 99%. That means that the benefit is really we're saving in terms of lives lost, that those lives lost will be reduced by 99%. And the damages will be reduced by 99%. So that's the benefit. And you then compare that with the cost. Now, obviously, in reality, it's a lot more complicated, and there's time effects and spatial effects and discounting and so on. But these are the basic principles. In terms of risk assessment, the most difficult part is to work out the risk reduction. That's where you need all the research and the computational power. Right? The rest of it is more economics and it's so challenging. But the reduction in risk, that's where the key intellectual challenge is going to be. And a couple of years ago, I worked with the ERC, European Research Commission, and we produced this book, Security by Design for Protection of Public Spaces. I was asked to contribute one chapter 6, which really spoke about the cost-benefit assessment. And I was really quite pleased to be invited to write this. I was the only non-EU member involved in this project. And it's really about a cost analysis. You might come down to the benefit to cost ratio. I said, you obviously want the benefits to exceed the cost, so you want the benefit to cost ratios to exceed 1. And so what we want to think about is the benefit can be the lives saved or damages averted. We have the threat likelihood, then the hazard, then the likelihood of loss, which is the vulnerability, times the loss. So that really assumes that there's existing risk. There's no extra protection. Then we have that reduction in risk, and that gives us that benefit. And we divide that, in this case, divided by the security cost. Or the probabilities that normally can be annuals, could be 5-year probabilities. It doesn't really matter what the metric is going to be. This provides the basic framework to assess whether a particular measure is cost effective or not. There's obviously uncertainties here, but if you get a benefit cost ratio of 1.01, that doesn't really tell you that much. But if you get a value that's 2 or 3, it tells you the benefits really exceed the cost, right? And so a protective measure is going to be worth doing. Just to finish up, I always like showing this video. Last year, from the Australian Research Council, I got some funding to look at car bombs. And what we did, we detonated 3 identical cars with the same charge. And we wanted to see what's the variability between each of the 3 blasts. Because these tests are expensive, people tend to do one test and use the data as if that represents reality, but we want to do 3 tests to see how the data varies from glass to glass. So, see if it works. Right, so we did this in the outback. So it was 800 kilometres from Sydney. The town we stayed at had 12 people. It was a little village with a pub. We got to meet all the locals. While we were there was a bushfire. We lost power for a couple of days. I almost missed a kangaroo on the road. It was a pretty adventurous weeks. And you can see the range here. I always like this tire. This just goes up there. And even though this was in March, it was really hot. It was like 40-degree, 45-degree days every day. And you can see that there's so I'm quite impressed that your facility is so close to here, 50, about 30, 40 k's. And because it was in such a remote location, we had to take 5 tons of equipment with us. We took 2 cars, 2 trailers. You're 150 kilometres from nearest decent sized town. So if you don't have it on the day, you just can't get it. So we're still analysing the data to give you a sense of distance. That's about 350 metres across, right? And some fragments ended up over here, right, 400 or 500 metres away. Okay, well, again, thank you very much, for your time, and again, Jose, thanks so much for the invitation to be here.
Mark, thank you very much for your very interesting presentation. We have time for only 1 question because we have the coffee break just prepared. So, any questions, Miguel?
Thank you very much, Mark. Very interesting. I'm not at all an expert in terrorist attacks, so I got a question. I think it was in slide 25. Just curiosity. Before just some yeah here. Because here we're speaking of an acceptable annual probability figure of something to the power -6, but normally, I don't know if this is related also to terrorist attack. Normally we're speaking about 10 to the power -4 as a general value. And so when I was seeing the figures, I was also thinking, it is difficult to say this is a conventional design is unsafe, really, because also in the terrorism scenario that you have introduced the probability, perhaps you could also say what is safe and then ask or inform your owner to say, okay, this is the probability that you can manage for a terrorist attack. So to do it inverse, to say, okay, that you could have 1 bomb you can spend every 3 years. Is this acceptable for you or not? Instead of saying this is not compliant. No? We have very difficult number to calculate the probability of detonation. I don't know if you did thoughts on that.
Yeah, no, I fully agree. I mean, I just do this as a very simple equation. I'm going to do this for industry, or I can hold an hour talking about this. But yeah, you're dead right. I mean, that's why I said it depends on the threat scenario, right? It depends on, I didn't show the table, but ISO 229 has a table that has consequences versus the cost of safety measures, and you can see where you think you are on that table. So here I chose catastrophic catastrophic consequences, right? So that raises the bar much higher. Right, for normal conventional design, you want 10 minus 5, maybe 10 minus 4. It bounces around that a bit. But I suppose the point here is that we can use a similar approach to measure safety. Right, we think about the hazard, the conditional failure given that hazard, and we can combine the two and compare them with existing standards to see where we are in terms of safety. But yeah, if you're talking to asset owners and government, then the threat isn't as simple as this. Right? There's a whole spectrum of what they think the threats are going to be. Particularly if it's only one building, a cost analysis doesn't really that useful, because they've already made the decision to strengthen that particular building, because it could be an embassy, it could be a a defence headquarters. So they just feel that for national security, we just have to strengthen it. But if you're talking about changes that will affect a whole class of buildings, right? So you suddenly think this could affect hundreds or thousands of buildings, then you need to have a bit more rigor and a bit more science behind it, just like in building standards, because suddenly you can't you can't have a measure that's going to cost a lot of money for a lot of buildings if you're not really getting the safety, and so the public need to get a good investment.
Upon the efficiency of the interventions that you have with the
yes. No, you did right.
Thank you very much.
So thank you very much. It's time for the break. We'll be back in 30 minutes. So we have coffee, orange juice. Okay. So again, we'll be back in 30 minutes. Thank you very much. Welcome again. So after this break, we have a new presentation. Sarah Orton is an associate professor and director of undergraduate studies in the Department of Civil and Environmental Engineering at the University of Missouri. The title of the presentation is Time-Dependent Behavior of Flat Plate Structures Near Collapse. Sarah, the floor is yours. So thank you very much for coming to Valencia again. Very far from Valencia, Missouri.
Well, thank you for having me. I'm excited to be here and present some of the research I and some of my colleagues have been working on. As with all research projects, it's not just me doing it alone. I put some of the names of my collaborators up here. Dr. Ying Tian from the University of Nevada, Las Vegas, collaborated with me on the first two projects, and Ahmed Ibrahim is on the third project. And then I have some postdocs and PhD students and some masters and undergraduate students. I didn't put their names up, but how it goes with research. All these projects I'm talking about here were funded by. There we go. And so I'm actually presenting three projects. One started back in 2012, dynamic response flat plate structures. I'm just going to give a very brief overview of that. Spend most of my time looking at time-dependent response under sustained loading. So you load it up and then see what happens. And then this last one is one I just got funded earlier this year, the impact of falling structural debris. And so far that's my talk here. The dynamic response to the flat plate structures, I tested 0.4 scale structures under sun column removal. And so you can see the idea with the structure here. We have a little segment cut out here, and then this is the structure. It's about 20 feet, which I'm not good at converting it to meters, but it's big. It's about the width of this room in terms of the structure. And then the columns, I have 9 columns throughout here that we then tested. And so, not going into a lot of details on this, there's papers about it, so you can watch the papers, but you can't watch videos in papers, so I brought videos. And so this was, we did 2 different column removals. This one was the exterior column removal. So we're removing this column right here. There's a little jack that's going to collapse. and it will drop. The applied load was about 10 kilonewtons per meter squared. The intact capacity, if you had the column, would be about 22. So you're about half of what the building would be able to withstand if it was fully intact. And you can see it didn't do so well. We did 2 previous drops before this at lesser load levels, and it didn't collapse, and so that's why we did the third. This other video is a slow motion video, and so the removed column is over here somewhere just off the screen, and then we're focused on the center column, and there's some LVDTs. The slab is right in here that you can see. And so it gets removed, and you see a nice punching shear failure. It looks clearer when the contrast is a little bit better, and then everything's dropping down. And so very nice video evidence of how it drops the speed, and the fact that it doesn't drop completely uniform. There is a little bit of rotation in it. And of course, that's what it looked like after we moved all of our extra weight. Very common punching shear failure. And Dwayne talked about this in department stores. The ideas of these columns sticking up and they're just kind of left there and then they fall over on top. Very common. Did another test, completely different structure. And this one, we're removing the interior column, this one right here. And so here is the slab, there's weight on it. This frame out here is just to hold a string pot going to the middle. And these other beams is the other researcher doing tests that put it in a way so we didn't get a good video. But watch this video. And I had them all timed at the same time almost. So this deflected and the neighboring columns punched. And so the columns that were to the side, front and back, they all experienced punching shear failure. But the after punching response, the post punching capacity was enough to stop the complete collapse. I think if I had just a little more weight, it would have gone completely through. A little bit less, I wouldn't have had punching failures. So it's like this little sweet spot right there. And this load was only 5.5 kilonewtons per meter squared, which corresponds approximately to 1 times dead load plus 0.5 live load. And so, as Mark said in most of his presentation, the live load is actually a lot less than what you designed for. So maybe it would have survived if it was a real structure, maybe not. So overall conclusions here is, for the exterior column collapse, you had to have about 40%. The strength was about 40% of the intact capacity. For the interior, a little bit more controlling there, 34% of the intact capacity. We also found that dynamic amplification factor was about 1.15. A lot of procedures say to use a value of 2, which is in structural dynamics. If you have a linear system, that would be the most increase you have from a sudden impact. Because this is acting very non-linearly, the dynamic amplification is actually quite a bit less, and that saves a lot of the structure. You don't have as much amplification. And then we also found that post-punching capacity can really stop the collapse. And most codes and things don't account for any type of post-punching capacity, but it is there. It can help. But you can have, we had discontinuous bottom bars, and they pulled out of the column. The top bars ripped out of the cover. There's lots of damage in the failure. Like I said, I was going to introduce this only briefly. There's several papers about it, so if you want to read more about the papers, you can always read the papers. The next project I'm going to go into more detail on is the time-dependent collapse behavior of flat plate structures. And so this is a project I just finished about 2 years ago. I'm still writing the last couple papers about it, so similar in publication. But it involved this idea that if you have a structure under some sort of sustained load, it's just sitting out there under gravity load, and there's some damage in it, it's a deterioration, somebody didn't design it right, whatever the cause. How does a sustained load affect the capacity of that structure? So we started out with some concrete material tests. We did some bond tests, did some modeling and things. We did tests of slab column connections, and then did a couple system level behavior models. And that. So I'll start out with concrete material. Concrete experiences creep. So under sustained load, you can define essentially 3 stages of creep. One in which the rate of strain decreases, and so it's a primary creep. Another one in which it's almost constant, and then a third one in which it can have a sudden increase until failure. Most concrete materials, some sources say 80%, some sources say 70%, but if you load it up a high level and leave it there, the concrete will fail over time. A lot of this research done very early by Rush And then our colleague here, Manuel, did some very nice work with his group recently, which we took and realized it worked very nicely. So I didn't have to reconstruct anything. Less than about 80%, maybe 70%, the cracks are growing slowly. Concrete does not fail. You have essentially linear creep strains. If you get to the higher one, then you can have rapid microcrack growth and a sharp increase in volume expansion, nonlinear strains. And one of the things that Manuel Ruiz did and his group is this idea of inelastic strain capacity. So if you look at the compression test curve and say that's what you would get under a standard cylinder test, then you load it up to maybe 80 or 90%, and then you would strain on that level and it would reach failure whenever that strain hit the descending branch of the curve, which I thought was a really eloquent idea, and it works. It's always nice when it works. So we did some of our own compression tests. There's a cylinder in here, put on some strain gauges to amplify the strain, put it under some nice big thick springs to create a sustained load, run the tests. And for our cylinders, what we saw is if we had a sustained load greater than about 71%, we reached failure. These were the same concrete that I was using in my test structure. It was a scaled concrete, so the aggregate size is about half the normal aggregate size. And so that may be why it was a little bit less. But you can see this test here, 68% didn't reach failure. This one at 70% didn't reach failure. And this one at 76%, it reached failure. And here, and this one at 71% reached failure. And so you can see about, you can also look at the strain rate increase. About 31% of the 20-day strain occurred within the first 24 hours. And so it really is that primary creep where you get most of the strain effect very early on, and then it kind of slowly goes on there. And the specimens that failed, there was definitely a tertiary phase where there was a sudden increase in strain right before failure, and it occurred in a fairly short window right before failure. And then this curve is my static compression test curve, and the ones from the long-term tests, you went up here, sustained loading, and then they failed when it hit the descending branch. It worked perfectly. This other one that went up here was the 69%. We needed to reload it and cause failure, so that was a little bit different. And otherwise, it's the data worked out. We can see the time to failure inversely proportional to the load level. We have a good understanding of the concrete material. So knowing the concrete material, the other question was, what about the bond? Reinforcement relies on the bond to the concrete in order to share the load. So is that going to affect the behavior? And so I did these beam-in tests where you have a concrete block. There's a reinforcing burrow going all the way through here. I have a jack to load it, and then when I put under sustained load, the spring helps to sustain the load. And this is a better test than just taking a cylinder and pulling it straight out, because I'm not creating any compression here. The reaction's back here, and so where I'm testing the bond, I don't have any extra compressive forces. I'm just leaving that purely to the bond load. The bonded length is just a little bit in here. All this other rebar had a plastic sleeve around it, so it was not bonded. There's only about 5 to 7 inches bonded within that. I pulled on it, left it under sustained load for an amount of time, and we had 3 specimens fail under sustained load at load levels of 81, 85, and 84% of their capacity at 19 days, 2 hours, and the one at 30 minutes. One didn't last very long. I remember the one at 19 days, I went out to check on it just to make sure, 19-day test, you want to make sure the computer's on and running. And I went and looked, everything looked good, everything was fine. I didn't touch the test or anything. I went to leave the lab, and then boing, it just failed. And so I went and looked at it, nothing was going on. I couldn't see any indication of failure until it just suddenly released and it slipped and it fell. So this tertiary phase, similar behavior here, you have an increasing rate, kind of linear, and the tertiary very quick before failure, and then the bond breaks out, and that's it. So sustained failure level occurring around 81%. Another thing that's interesting in this is the additional free end slip was about 124% of the initial slip. So you load it and move some, and then over time it moves that much again and a little bit more. And so you're talking about a whole lot of slip in the connection even before failure. And so that is part of what causes increasing deflection in our reinforced concrete structures, a slip between the reinforcement and the bond. And the concrete. With all that information, can do some material modeling. We developed a user-defined material in ANSYS, and so my PhD student developed it. I was mostly out of it at that stage. Did 4 different stages, looked at the smeared concrete model, model looked at viscoelastic behavior under sustained loads. To do the nonlinear creep strain effect, we used the previous research. It worked out really well. And then for our bond model, we based it on some of the previous research and then applied it to our own data. Did some failure criterion, applied a hardening rule, applied a plastic flow rule. And then for the bond model, we took some existing bond models and then looked at our data and were able to fit a equation here. And these coefficients 4.85 and 7.41 were coming from the best fit from our equation. And so that allowed us to predict the bond slip. And there are other variables in here that you could include with temperature and size effect and humidity. We didn't test that. We just used what was already published on that information because all our tests were at pretty consistent humidity. But the model worked really well. These are the bond tests, and then the predicted model is not perfect. It's hard to model bond, but I was pretty happy with overall results. And so we did models of some reinforced concrete beams. I did not showing those tests here, but I have a paper out about the beam test, just about 4-foot long beams, about that big, about that size and cross section. Modeled those beams, compared it to the experimental data, and the differences are fairly acceptable for this type of work, especially under sustained load. Then we also looked at the strain and the time to failure, and pretty decent work. One thing that I thought was interesting is we looked at this particular test where one model we considered that bond model, and then this model here we didn't apply the bond slip effect. And you can see a very different increase in the creep deflections with time. And so just applying that slipping of the model, at least in these beam results, was able to help us get the model results to match the experimental a lot better. Last set of tests we did was these isolated slab column specimens. And so you have your reinforced concrete slab here, and then you have the column in the center. The slab was, I think, 3.5 inches. What does it say here? 89 millimeters. That makes sense to you. Just typical reinforcement, nothing really too special about it. It did extend beyond the inflection point. This is where the inflection point would be in the real structure, and I extended it beyond it so that you could include any compressive membrane effect that would be used in the slab as well. These tests, again, we're putting under sustained load. Most of the tests did not fail under the first sustained loading period. So we'll load it up. This one was to 89 kilonewtons and leave it under the load for like almost 45 days. And then if it didn't fail, we put a little more load on and leave it on the load, leave it under the load for 3 days. And it didn't fail, you put a little more load on. Just kind of incrementally approaching that to see when we could get that sustained load failure. Most of them didn't fail under the initial loading. This one did. This one only failed. It took 20 minutes. We loaded it up, and 20 minutes later, it was failed. And this last one, we put it on the loading, and it's about 30 days. It's like, oh, so we reload it, and it failed very soon after. So very hard to get the level of loading, but the capacities, it was able to hold the sustained load for about 3 days within about 5% of the capacity. So I had to get really, really close, kind of inching up on that capacity in order to get that failure to happen. We looked at the bond and the concrete, and they were saying, 70%, 80% of the capacity. With the reinforcement acting in there, you can get really close to the actual capacity. And so it's reassuring for our structures that they have that ability. So these are some of the tests. These are the ones at a 0.64 reinforcement ratio. So nice behavior here. This black one was the controlled tests, and the blue and red ones are the sustained loading tests. And it's really hard to tell the difference. I have some boxes in here where it's under sustained load. There's definitely increases in deflection under sustained load. But when we loaded it, behavior is pretty much matching the control test. Not really an increase in capacity, really no change in the deflection at failure for this lower reinforcement ratio. For the other tests, we did a little bit cut off here, but 1% reinforcement ratio is a little bit higher reinforcement ratio. And in those tests, the black one's the control, and you can see the test ones have about the same capacity, but the deflection at failure is around 22% higher than the control specimen. The ones with the higher reinforcement ratio tend to be controlled more by the shear behavior, but under sustained load, because the concrete's creeping, it's allowing a lot of deflection. And so you're able to pick up a lot more deflection in the ones with the higher reinforcement ratio than you would under short-term loading. The deflection under sustained load followed pretty much a logarithmic trend. And so same behavior that you saw in the bond and the cylinder test. Initially, a lot of deflection, and then kind of tapers off with time. And you got about a 40 to 80% increase in deflection under sustained load. And so whatever it did initially, about 40% more deflection under the sustained loading period. But interestingly, the strain that we had in our reinforcement, the deflection increase here was only about 20%. And so even though the specimen was deflecting about 40% more, the strain and reinforcement was only picking up about 20% more strain. And I think that is due to some bond slip, some slip in the structure, allowing it to redistribute the loads, and not all the load that the concrete's losing is going into strain and reinforcement. Another thing that we looked at is there any warning of the impending failure? And so these are just examples, some of the tests. About 200 seconds before failure, I can see there's an increase in deflection, a little bit of a drop in the load. The load's not a lot of drop, but there definitely increases in deflection. But you're talking about 100, 200 seconds. It's not a lot of warning. There's not going to be some things like, oh, I think this is about to fail. Let's go talk to the structural engineer and see what he feels. No, it's going to go pretty quick. And so this is a video. This was the test that failed in 20 minutes. We were loading it and watching it, and we noticed it was really soft. Every time we put on load, it just kind of went away. And they're like, well, I think this test is going to fail pretty soon. So we were able to record it. And so let's see. We can watch it here. And so we loaded it by just tightening these nuts here.
Yeah. Okay.
And we're like, okay, wait, we think it's going to fail. And then it made me jump, but that was the failure. I mean, you couldn't see anything going on. The only reason why we knew it was about to fail was that the load kept dropping off. It was like, this is indicating that it's about ready to go. And then it just went on its own. Did modeling of it, of course, using the ANSYS model, used the same configuration of the model that we did in the beam test. We tested it out in the beam test. We applied the same theories and ideas to our slab test, and we're able to get really good results. We didn't have to modify the model, do lots of changes to match the data. Once we got it set with the beam tests, it worked out really well. Some differences, I mean, one's about 12% there. But, whoops, trying to hit the laser pointer. But overall, for a model of something moving under sustained load, I think got some pretty good agreement. Did some parametric studies to see if the influence of the concrete strength, not a big influence in concrete strength, increasing a load level, can increase the deflection, but it's not a huge increase. Increasing the concrete cover can decrease the deflection, but it's not huge. And we saw that we would get failure if we had a load level of about 94% or above. If we had lower load levels, then it wouldn't eventually fail with time. And so 94% is a lot of the structural capacity. It's way more than you would ever put on a realistic structure. You want some safety factor in there, but it's really hard to get that load level just right to cause failure. And so we took a test done by Morel out in Forditra, and they had a test where they removed a column and it deflected. This is actually 4 hours after the test. 4 hours later, it had punching shear failures at these connections, and then they're like, okay, it's fine. They went away. Overnight, it completely collapsed. And so it's this idea of under the sustained loading, it initiated a punching shear failure, and then it collapsed overnight. And the model was able to match that fairly well. They didn't have a lot of data at the collapse because they shut everything down and went away for the night. But I think the model, I was able to match the results fairly well. And so what I learned in this test is, concrete itself, the material that we had experienced failure about 70%. Concrete is susceptible to creep deformations and failure. When I look at the bond, then I had about 84% of the capacity, and I had a lot of slip as well, a lot of slip in that bond. And so when I did my models, I need to apply that bond slip model. That worked out a lot better. For something like a slab column connection, when you add that reinforcement in it, the reinforcement does a great job of taking up the load that the concrete's losing under creep. And so you get up to about 95% of the capacity before you get sustained load failure, which makes me feel a whole lot safer. Most structures have reinforcement. The reinforcement is going to be there to help me help take care of things. Increase in deflections, definitely a lot of increase in deflections. So this is idea of monitoring the structure. They always monitor deflections. There is increase in deflections. It's not as much as the bond, 23% initial, but you can definitely see increases. But the impending failure, when it's just increasing and it's about ready to go, there's very little warning. You have a very short time window, which would be a problem if somebody's just sitting there monitoring it. It's like, when do we actually have to leave? Once you're worried about it, you should go. And then lots of papers about this. Some have been published. One has just come out in structures, and so that's the one on slab tests. These other two relate to the numerically. I'll get those out. My PhD student graduated without publishing his papers, which I probably shouldn't let him do. So all your PhD students, anyone out here, make sure you publish before you leave, because trying to get you done afterwards is difficult. And then my colleague Ying Tian, he did related tests on columns and beams, and he has some published work as well. All right. So that was the second project. Now I'm going to introduce the third one here. Let's see, I still have time. And so this is a project I just got funded. It's the impact of falling debris and structural collapse progression. And so the idea is looking at if I have some sort of connection, it fails, and I have this slab falling down on the floor below it, how do I analyze that impact? What type of forces am I looking at? And this does happen. There's the Pikers Road car park that collapsed. There's a Hard Rock Hotel in New Orleans, lost several floors. How does it progress vertically? And can I actually stop that if I know the amount of load? And so, like I said, this one just started. We don't really have any results, but if anybody out there has ideas, I'd be happy to learn about ideas. So we want to prevent collapses, and we set it up in a series of 5 tasks, and so I have some more slides on that. The main fundamental questions that I was looking at here is if you have something that is going to fall, what's the velocity, shape, and condition of the impacting mass? Most of the time when you look at falling debris, you're assuming it's falling at free fall through the entire story height. But just like the flat slab test I showed you, a little slow-mo video, it's not at free fall. You have to lose the connections. It slows it down. It's not flat, it's doing it at an angle, so the impact is not all at once. It's going to be more gradual, and then the slab itself might be damaged as well. If you have, for example, a drop of water hitting something versus a drop of ice, the water is going to impart a lot less impact energy because it can distribute. The ice is going to hit a lot harder. As most impact tests are done with steel impactors, not a lot of ability to distribute there. And so let's look at that. The other question is how much energy is lost on impact. Usually impact is bounded between rigid, think of billiard balls, really hard balls hitting each other, they hit and they bounce off, versus plastic impact, something that's really soft, it hits and sticks together, right? There's 2 different bounds of that. Well, where is concrete in between that? And then what's the dynamic response of the impacted beam? And so what's the actual capacity of that beam under that impact load? That one's a little bit more better understood because there's been lots of blast tests and things. But all of this together, we don't really have the answer. Most of the assumptions they use in trying to evaluate falling debris is very conservative. And so you're assuming free fall height, you're assuming it's impacting all at the same time. It says if I had something like this Piper's Row car park here, and you analyze that, there's no way the floor below could have survived that impact. And yet it did. And so is there a way we can be perhaps a little bit less conservative so we can actually design something that will work? And so been doing some preliminary studies, took a frame test that I did earlier. This is just a frame here. Pulled out the column, and you can see it fell, and there's lots of clanging sounds. Made some models of that, and the experimental velocity was only 70 inches per second right before the catenary action took in. The FEM model said it'd be about 42. If you assume free falling, it's about 123. And so that right there shows that the velocity, the speed at which it's going, is much less than a free fall velocity. So you can see the difference between the velocity and free fall. This is where the velocity started to slow down because it caught itself in catenary action. But still, definitely a difference between what the frame was experiencing and what the current assumption is. And so can we do better with our analysis? Also looked at the shape, and so if it's in the model, if you assume a uniform, everything hitting at the same time versus something at an angle. And so if you're assuming it's at 45 degrees, then you have 39% of the impact force if it's hitting at an angle versus something hitting all at the same time. And so again, this is something that is perhaps overly conservative in how we design things now. Maybe we can get some more accurate numbers for some testing. And so one part of this test is we're going to analyze some drop beam experiments. We're going to have a beam hanging up here that's going to impact this beam. It's going to be done at different angles, different concrete strengths, different velocities, and currently trying to figure out how to design this test setup. So it's a nice little sketch. I have no idea how it's actually going to work. But if you have any suggestions, let me know. Going to do some FEM analysis. We can't do all the tests, so we can analyze more velocities, more impact strengths, concrete strengths, different types of precast connections. Once we get the model up and running, then you can do a lot more analyses. And then we're going to use the applied element method to examine some prototype cases. And so we have some knowledge from our FEM models from LS Dyna, and then prototype cases, flat plate, precast, and then modifying it to like, or maybe it's a light roof construction versus something that's heavy. And then hopefully once we do all that, analyze the results and come out with something that would be some sort of simplified methodology that I can say, well, if you're analyzing collapse for a flat plate structure, the velocity should be this percentage and the impact energy should be around this. Something engineers could use to help them check for falling debris impact. So good analysis tools, and that's going to give us the ability to determine if the collapse going to progress due to impact. So if that interests you, let me know. And as we proceed with the research, there'll be more papers about it. My PhD student will publish the papers before he graduates. And so that's upcoming. And that's all I have.
Sarah, thank you very much for your presentation. Also, you see, the PhD students, it's important to finish the work before leaving the university. So that's a key aspect. So we have time for questions or even suggestions for your test. Okay? Any questions for the audience? Or even a suggestion for the next experimental campaign?
If you don't want to talk in the room, you can find me later and ask questions. It's fine.
Questions in the other break, okay? So thank you very much, Sarah, again.
Well, thank you.
So our next speaker is Renata Obiala. Renata, I can see you. Okay, sorry. So Renata is a head of construction and infrastructure applications department in global R&D at ArcelorMittal. The title of the presentation is Material Design in Harmony, the ability of structures to resist hazards. Renata, the floor is yours. Thank you very much for coming to Valencia.
Thank you very much for inviting me for this event. Thank you very much for your hospitality, Jose. Okay, so let's talk about material and about design. I hope I can use it. Yes. I would like to start from the end. What is the hazard? And we heard already a lot about this, about different type of hazard. As you see on these pictures, I would like to concentrate a bit more on the natural hazards and why. Oh, wrong direction. That's also hazard. Simply because due to climate change that we face even today or last week, having the highest temperatures recorded in April ever, the events become more frequent, more severe, and we need to act faster. What can we do? But maybe because before what can we do, let's move to some statistics. Already now, 80% of cities worldwide are reporting that they are affected by climate change in different ways. They are affected by the heat, they are affected by the sudden rainfalls, by a lot of flooding or of drought. That's happening. And of course, the policymakers, environmentalists, industry, all of us are not remaining passive. We try to do something, what we can do. We have a lot of campaign related to climate change with also very, very different focus. One of them, Race to Zero. This one is focused strongly on the decarbonization, on the reduction of the gas emissions, CO2 emission to the atmosphere. Another one in the same group, Race to Resilience. This one is focused on the people, on the nature, how they are impacted, how they are affected, how they can be protected. Okay, we already have the word resilience here. So now, as I think all of us or most of us are engineers, let's talk a bit more about design for resilience. So this is where we should make a difference, make an impact, do something to help ourselves and help the environment. So resilience, this we heard also from Mark, it's about probabilistic approach, it's about the, is it a risk, it's not, so it's something about managing this uncertainty. And of course, we don't know the time, we don't know the intensity of the events, and we predict it to some extent, but very little. But maybe we can predict how the structure behave. That's what we as engineers like to have. We have it under control. Huh? So here we can a bit more control what's happening. Of course, thanks to all the research that is going on that happened before, what has been presented has enormous impact on our ability to predict the performance of the structures. And here I think nobody will be surprised that I move a bit to material and I focus a bit more on steel. Steel as material is known for centuries all over the world. I just give you a few examples of what has been found 3 centuries before Christ, 11 centuries before Christ, but all this steel was not used for construction, for a lot of different uses, but not for construction. When things change is when it was possible to remove all the impurities from the material, industrialize the process, and basically produce it in sufficient volume to introduce it in construction, also having the right quality for it. So how do we produce steel? Traditionally, or well, one of the first processes which was industrialized is producing steel through blast furnace route. I marked here one number. We need 1.3, nearly 1.4 tons of iron ore to produce 1 ton of steel. In this process is what we hear also in media a lot of gases, a lot of carbon footprint, a lot of CO2. Yes, that's the process, but steel industry doesn't stay passive. So now we produce steel through electric arc furnaces, which basically melt steel again, melt scrap to produce new products, new material. Here, what is important to mark, it's the amount of electricity which is needed next to the scrap to produce 1 ton of steel. It's again enormous. And here, this electricity is responsible in a sense for the carbon footprint. So since I'm talking about this, and this was already mentioned, I cannot avoid not to show you the level of recyclability of steel. The very careful observer will notice that there is some mistake in the sum up. I think it's not carefully checked roundings, but okay, let's say nearly 97, 98% of steel can be converted into new material. Around 2% becomes waste. And now coming back to the production routes, how does it look like? We had some discussions yesterday why it's such a big scattered when we are searching for the numbers. What is the CO2 emission in steel production? So the very traditional route, the blast furnaces, you have nearly 2.5 tons of equivalent CO2 emission in production of 1 ton of steel. The technology improved a lot. And you see already by introducing the first electric arc furnaces was reduced very big step. But this doesn't stop. We introduce more modified where we use nearly 100% of scrap in this production. And even further, where the electricity plays a role, using fully renewable electricity, the impact, the CO2 emission is on the level 0.3 tons per ton of steel. In Luxembourg, well, a lot of plants from ArcelorMittal is producing through this route, especially for construction. In Luxembourg, it's 100% production in this way. We call the steel X-Carb. It's fully recycled and renewably produced steel. Okay. Coming back to steel, what is steel? It's a very simple mixture of iron and carbon with a bit of additions. Why we say steel, why I present steel here on this workshop, it has properties which are very important for building for resilience. Oops, too fast. Its high strength is ductility. There is stainless steel, which has resistance to corrosion, high durability, easy to move, easy to assemble, and easy to sell. Okay, let's focus a bit on high strength steel. So high strength steel, why it's important here in this aspect of resilience or improving performance of structures, it's important because we can, keeping the same weight, increase the resistance, which means we don't need to make the building heavier. We can use higher quality steel, keep the same weight, and have higher resistance. In the other way, if we want to reduce the weight, we can also optimize it. Thanks to the advanced technology in production, the QST route, we can also keep the same strength of the material, even for very, very thick sections. So you see the thickness of the flanges is up to 140 millimeters, and we can keep the same strength all over the thickness. That's about high strength steel. And now I would like to move a bit to the examples and solutions. How we can use it for different aspects related to robustness, to resilience, to hazard. Let's continue with the high strength steel, maybe for bridge applications. In our center, it's for a very long time we are developing different types of bridges with different solutions, using, for instance, Preco-beam system, which is very special shear connectors, allowing for a bit more slender bridges, arch-tight bridges, which is a very big focus nowadays for our development, with hot rolled section instead of welded plates here. Um, these bridges are usually, even that bridge in general, we consider this as very a monumental structure. We have very few all over the world which are very long span and very monumental. Most of the bridges that we have are medium short span 10 to 45 meters. So they are simply practical. They are fast for reconstruction after natural disaster, after flooding. They can be very quickly built. Uh, this bridge can be made as modular bridge. We have examples that the bridge were installed for railway application overnight because this was the only way to stop the trains running. So one night the bridge had to be there, functional and fully made there. Again, about the bridges, it's also not a secret that fatigue is the something which is driving the design for bridges. Here we were testing new hangars for the tight arch bridges. And again, because we used high strength steel with very thick sections we called jumbos. You can see here it's a colleague who is finishing some element for the testing. It's really big section. We had to test this part for fatigue. The performance was surprisingly good. Well, it's the right word to say surprisingly. It was very good. It exceeded several times the requirements of the standards. So we can say we have extra capacity here. The bridge can last longer. Of course, has to be monitored, has to be proven, but in principle, can last longer than the design lifetime, which is what we really want. It was also done numerically. Here is maybe worth also to say it's a machine for fatigue testing called Chronos, which allows to have to test very big specimens used very often for offshore application, where also these fatigue aspects are very important. Okay. The last slide about bridges. Here is again a new element that we were developing is the connection between the bottom line and the arch of the bridge. This kind of hanger, usually they are quite vulnerable against wind because they are flat in one direction. So depending on the direction of the wind, they have bigger or smaller resistance. Here they are a bit twisted, so it's like put one into another, giving much more resistance against strong wind independently on the direction of the wind. And here we had some CFD simulations and analysis to investigate what is really the resistance of such hanger. It was done for a specific product, but the analysis allowed us to extend the findings, the conclusion to general recommendation against the standard. Okay. I will stay with the high strength material, but move a bit to buildings. And why is it important? Some time ago, I found this. We had a presentation from Professor Anthony Wood from CTBUH, who showed us a bit of statistics about high-rise buildings. I have to say, I was a bit astonished. Didn't realize we have such a numbers. Buildings above 200 meters. In 2020, we had 1,722 buildings of this height. In the year 2000, we had only 263. maybe we don't realize it so much in Europe, but in US and especially now in Asia, they are booming. It's enormous number. And now, why high strength steel? Because it allows us to use half of the material for such building than in the past. I think this is not the last word. It's not stabilizing. With the increase of population all over the world, this number will also grow. So it's important to keep these buildings also relatively light, but relatively safe. So here we had development already for a long time, as this is a very, very complex thing. And this was also highlighted a lot in the previous presentation, how important are the columns and the transfer of all the load to the columns in case of collapse. So it's about columns. Columns composed from jumbo sections encased in concrete. You can see those were tests made in China in the, if I'm not wrong, scale 1 to 3. And here is a person standing in front of this specimen. So normally the specimen is 3 times bigger, at least 3 times bigger in real building. We had to do it in China because there was the only lab which was able to somehow demolish this, crush these columns. They are so massive. And still, despite of the scale effect and so on, we still try to as close as possible to reality to get some conclusions to understand how interaction between these steel sections, which are not connected, nevertheless work together. The load is transferred through the concrete, through the stirrups, through the bars, and so on and so forth, that we have a solid element and we have a really safe structure for the high-rise buildings. I'm happy to say that we are going now through the peer review process of the design methodology, which is now to be signed off, and we'll start developing a software which will help to at least redesign this kind of structures. Staying with buildings and this time with the seismic application, this solution, I think I can skip it because it was already mentioned a few times. It's also a solution has been developed in collaboration with University in Liège to ensure that the failure is in the beam, not in the column. And again about seismic. This was European project INERT, which was inspired by the failure during the seismic earthquake in Turkey. You see in this building that the ground floor, the first floor, is not existing anymore. It's this soft story effect that this part is collapsing. It's a reinforced concrete building. In these buildings, as some statistics says, 90% of damage happens here. So what has been proposed is to give a bit more ductility to this solution by inserting steel inside of the column at the bottom floor. So it's also to avoid the punch effect, the steel goes a bit above the slab. So that's to avoid the failure, the progressive collapse of this kind of buildings. And now moving a bit to fire, I want to present you a system with composite beams. Naked beams. It's not fire protected beams. Don't know why they use the naked form, but okay. Those are the central beams in the bay. Then we have reinforced concrete slab or slab with steel decking. Important is that the design of the reinforcement is a bit more than for normal design, and all the beams which are around the perimeters of the compartment of the cell are fire protected. So what's happening when we have the fire? The buildings, the beams around as fire protected are not deforming much, but the beams in the center without fire protection, with time, they basically totally lose their capacity, their bearing strength. So what we have here is basically development of catenary action. We say we have the failure which leads to the increase of capacity. It's a bit bizarre, but that's what is happening. We are losing the beams, we are activating the slab. What is very important is the level of the reinforcement in the slab, that it can create the tension ring and the membrane effect. For this system, there is also available software to help design this kind of things. Commercially, applying the system, we allow for a reduction of 30% of the fire protection, which is basically reducing the cost of the structure without really compromising on any safety here. Floods. Yeah, you see by yourself, currently 2.15 billion people live in the near coastal zone. 898 million people in low elevation coastal zone globally. And what I learned yesterday, also Valencia was affected by flood in the 50s, which made the city to be completely changed, to provide a lot of dams and features which prevent that it happens again. So what can we do to prevent flood? And here we have solutions with the product sheet piles. I should have showed the picture of sheet piles, but this is a system like this. Steel elements which are connected together, encased in the soil, basically resist a lot of pressure. They are used on the coastal zones. They are used a lot in the Netherlands, where they have naturally problem with flooding being close to zero level or below. It also showed very good performance when the sea is rising due to storms, hurricanes, and so on. And why is that? I hope I have the. It will be possible to run the. Thank you. So this is test that has been done by some in the Netherlands, funded by some national research fund. You can see a row of sheet piles here. Behind the sheet piles is a lake, and these containers create additional load. And you see with the additional load which is put behind the scene, let's say, all this wall is expanding, but not breaking. It has enormous ductility thanks to material, but also thanks to the geometry. So these systems prevent failure of the whole dam, of the whole protection wall. Here also a lot of measurements have been done, and the processing of this, it's a lifetime job, but we have a nice video that makes the first good impression. At the end of the presentation, I'd like to come back to the bridges and also to highlight that, okay, we do a lot of things to mitigate risk and so on, but really the prevention is what we need to focus a lot on. And here I wanted to present you dolphins. So again, systems which are made from sheet piles, which are used mostly to prevent impact of the ships, containers on the pylons of the bridges. Something very, very important, as we learned recently, especially when the load on the rivers is changing, we need to protect this kind of structures. In our team, we work for a long time on different projects related to robustness, related to impact, to blast, projects like COSIMP, AdBlast, Robust Fire, Robust Impact. All these projects or the outcomes of these projects were finally put together, creating guidelines for robustness in the project Fail No More. The idea here was to make something simple. We were not fully successful here. It's, as you showed today also, this is not a simple subject. So we cannot have a simple design rules. And also it's what a lot of people highlights when they have contact with designing of important buildings, strategic buildings. We don't want to provide guidelines showing where are the weaknesses of the buildings. So in a sense, this project proved that this subject remains complex, which opens a lot of possibilities for further research. Nevertheless, addressing individual events, individual risk, we can provide solutions which are helping the buildings to survive. And I think that leads me to the final slide, to the summary. So with all these failures that I showed before, all the hazard at the end, we want to have solutions, and we are on the good way to have them. And just to summarize what I show, resilience, managing and preventing hazard is very important for society, for all of us. Research in this field is very important as health and safety is a global priority for all. Material in design have to work together, provide an efficient solution. Steel is a modern product, not only material, and highly reusable and recycled. Steel provides solutions to hazard, to resist hazard and save lives. As I said, I focus on steel, but we cannot live without other materials. It's like the example with fire. When the steel fails, we rely on the slab. So we need to use all the materials we have and the best features the material have in the wise way. And that's it. Thank you very much. The most important message. As engineers, we can contribute to safety of our environment, living and working environment. You see, the most important, I would miss it. So now you will not forget it. Thank you very much.
Renata, thank you very much for accepting the invitation to visit Valencia, the workshop, and for your very interesting presentation. So we have time for some questions. Any question? You see that we combine different topics. First, a general topic on endure, concrete, risk, steel. So, Renata, thank you very much.
Coffee break is, I think, better place.
Do you need a coffee break right now?
No, I'm saying that this is
Okay.
to discuss.
So good. Thank you very much.
Thank you.
So Miguel, are you ready for the next presentation? Our next speaker is Miguel Fernádez Ruiz, and the title of the presentation is Extreme Event in Flat Slabs, Past and Ongoing Experiences with a Focus on Punching Shear Resistance. Miguel is a professor at the UPM, the Technical University of Madrid, and he is a professor in the chair of structures, and he's also the vice dean for research in the Civil Engineering School in Madrid.
Tiene animaciones, tienes que aceptarlo. Sí. There's no viruses in the presentation, so.
Ready, Miguel?
Okay, thank you. Thank you very much, and good morning, everyone. So I will speak now on this presentation on extreme events in flat slabs. So some past and ongoing experiences with a particular focus on punching resistance. And I would like to thank Jose for this invitation, for this very nice workshop. And also when he asked me about a presentation, he told me something interesting. He said, "Why don't you start saying something on also on your group, what you are doing, what your experiences?" And now while listening to the other speakers, then I think this makes a lot of sense before we go into extreme events, so that we can see what are the connections and what are the exchanges that we could have. So just as a brief overview of what what I'm doing and where I'm working, and also what are we can see that even if it seems that I might have different background than the other speakers, we are all working on very similar topics. So I'm working at UPM, so which is it's in university in 1971, but that is gathering schools from some of the oldest schools actually of civil engineering. For instance, it was at the beginning of the 19th century. So it's a quite largest university, 35,000 students, where we are almost 300 professors and researchers. We have a couple of buildings. In, I think in Madrid, we are developing something which is very nice. We are working closely with industry. So it's not only academia, very working in an isolated manner, but working in close collaboration with industry. I think this is one of our strengths, and this is why we are we appear in these rankings quite high. We are currently eighth in the Shanghai ranking, so in Europe after Zurich and Copenhagen. And what we take advantage, and this you will see why we present this later, of some large experimental facilities. I really think that testing is a good way of advancing knowledge. So pretty much like also Sarah was showing, and we could test, and we will see later this, that was not a test by me, that was a test by Alejandro Perez Caldente, real buildings in the lab, also removing tunnels, but large size specimens. We also have devices for powers for impact loading. I don't know if you could run the animation, so that this is also, this is not also a test of mine. This is Carlos Tanui and Gonzalo tests, but we are equipped also for testing in case of extreme events. If I, okay, now. And we have now completed also building of some peculiar experimental facilities. This is the what we call the multi-axial structural tester, which we have finished right now, which allows quite large elements as it would be a slab by putting membrane action, so up to 2 meganewtons in horizontal direction and 5 meganewtons in the vertical one. So this is aimed at testing really at the structural level what's happening in reality. And with respect to some lines where I've been implied, and this, I think this makes the link to the previous speakers, even despite our differences in background, I feel that we are working very closely. So topics of sustainability, and this is something very interesting. Renata, this comes very close to your presentation. So we are, for instance, investigating what is the impact in terms of kilograms of CO2, so carbon footprint per square meter built. And we have seen that concrete that has been very poorly treated by press, for instance, and by public opinion, because it has high footprint, is not necessarily the case. So it depends how you use it. It's a matter of the structural efficiency. So if you start using a waffle slab or drop panels, you start using much less concrete, and you can use also composite solutions or timber solutions, and all of them, they might work with a similar impact, in fact. So it's not only timber, the right manner of building. It depends on how we use our construction materials. It's a matter of structural efficiency. Also, we are very active on reliability, Mark. So this time goes to you. And we have been basically also in Madrid. I want to discussing what's the good value for beta, what is the level of reliability that we have to adopt, not only for new structures, but mainly for existing ones. So what to do with our existing structures. This is a topic that I will come with this image at the very end. And also we work on the structural level. So, but it comes from the material. So this is the same figure almost now that Sarah was showing before. That's one of my first papers, which actually came this idea of the inelastic strength. It came not from grip tests, but it came from when I saw some low cycle fatigue tests. Not that they were doing low cycle fatigue tests, and I saw that failure was happening when they touched the monotonic failure envelope. And I said, okay, that's the propagation of cracks inside, and then is there a link with creep? And that's where the idea actually came from. These models, we can implement them. This is the thesis of Rafael Ruiz, and now we're testing these elements. And the idea is always to apply them at a structural level. So this is a pavilion that we built in textile reinforced concrete. All you see here, this is not steel. This is textile reinforced concrete, and also the shells that we built in Fribourg at EPFL when I was still there. And we are also working on limit analysis, strat and time models. This is something that I work closely with Jaime Mata, which is also in this audience. And we are working in FIV, working party 2 to 4. And finally, this is the topic that I will develop now. This is the flat slab response. And we will be seeing some topics on resilience, but I'm very much interested in real size testing. So I was not implied directly in this test. I think Andri was the key person working in that one. That was a previous research project in Europe. But now I am implied, very much implied in this one. It's a European project led by Antonio Pinho Ramos from University Nova in Portugal, which is taking the same dimensions as the previous test that was a slab stress, and this is recycle slab project. So it's 14 times 9 meter, and it's going to be tested in punching and also in dynamic response. So yeah, this a bit, as you see, there's having an overview is very wide, and I think that's good because it helps understanding what we are going to see now more in detail with respect to the topic on extreme events in flat slabs. And as also many others, I have to acknowledge that this is never one-man work. So I'm working at Polytechnica, and this is something I'm doing in close cooperation with the University of Surrey, with Juan Sagaceta. I know that here there is a close link also with him, particularly with a postdoc working now with Juan, which is Maria Liapopoulou. And we are developing and extending some previous models that we will try to clarify now. So why is this topic important? So it is, as Sarah was showing in one of the videos, no? I think it's very important to note that when we have a flat slab and there is a column removal, the most probable mode of failure would be punching. Punching is normally governing at the ultimate limit state. Serviceability must be deflections. But when we have a column removal, we have increases of the shear demand in inner columns and also in lateral columns. And also we have increase of rotations, we have increase of the level of strength that we are having. And this makes that the columns are prone to punching. So punching is this, when we are developing these inclined cracks inside the concrete, and it happens in a phenomenon that what we call is localization of strength. So the strengths, they are localizing within one that we will call critical shear crack. And this critical crack is going to rule the strength. And something curious in punching is that you may get the same localization in here, but in here you can avoid the localization by placing a stirrup. However, you will not avoid localization in punching, even if you place lots of stirrups, because in punching there is also an effect on the internal forces. So the shear forces, they are increasing a lot towards the column, so they're going to infinite. If the column was zero size, the bending moments are very high, so they are concentrating near the column. So even if you provide lots of reinforcement, you will get localization of strain. What is the consequence? Is that you get brittle failures. So even if you have low amounts of flexural reinforcement, it will come, this is what we are going to see now, a moment where it fails. And when it fails in a brittle manner. And this has consequences because this sudden loss of strength and the residual strength that you may find, they're not sufficient to arrest a progressive collapse. So once this, a numerical simulation at the time, once you lose a column, then the load is going to be transferred. These are the shear fields, corresponding shear fields. They try to be transferred to the surrounding columns, which increase their action, and then they punch, and in turn, now they punch the others, and it extends, and then you get a progressive collapse. So punching is can be propagated, and it's hard to arrest. Actually, it's hard to arrest because they always localize at the same things, and this is why I think the interest of this endure project is of high importance, because even though we can provide some elements for integrity so that the debris, they are not falling on our heads, but we cannot, we're not capable of arresting almost the punching failure. So unless we provide new strategies, new views on how to do it, perhaps with this fuse segmentation strategy being investigated here. So in order to understand now what happens and why is this working so, I will use the critical shear crack theory. So this is a theory that was started by Professor Mutoni many years ago, but now it has been worked by many people from academia from all over the world. So there are people developing in Portugal, in Spain, in the UK. Okay, Andri has also worked a lot in this theory. So there is a joint effort of many people now. I think this is a very good way. It is based on assumptions. They are easy to understand, and so we can all contribute to it. So in fact, everything is written here. And so what is the theory saying? That the strains, they are localizing in a critical shear crack. This is what we were seeing before. Despite that, even we might have shear reinforcement. And then it's simply saying, okay, this critical shear crack, through its shape and kinematics, so the way, the shape that it is having, the curvature it's having, and the location it's having, and the kinematics, it will, what is the capacity that we can transfer through compression struts that we are having below, aggregate interlock, so friction between the lips of the cracks through the crack. Residual tensile strength, well, they are related. One is mode 1 and the other is combined mode 1, mode 2. That one in action just on top, and eventually if shear reinforcement is available, also the contribution of shear reinforcement. So it's very simple. You say, okay, you just consider you have localization, which is true. You will adopt a shape and a kinematics for that, and then you just integrate what are the contributions, and you will see what the resistance is. So these simple ideas is what we're seeing here. So when we start loading an element, let's imagine that it's a very slender one, and then we're having low shear demand, we will be having flexural cracks. So if we try to reproduce what would be the acting shear force here at the column, and what is the rotation as an integral of the deformations that we are having, we see that we are starting to have more and more increasing levels of deformation for increasing levels of shear. In these camps, even that we could yield the reinforcement. But even if we yield the reinforcement, what happens is that eventually we'll have that the cracks, they are so wide that they have problems in transferring shear. So the crack will disengage, and then we will have a penetration of the column. This is exactly the video that Sarah was showing. So we can start with a crack, which is opening in a flexural manner, and then it punches, it penetrates. So this is what we call a two-parameter kinematical model. So it is depending on the rotation and also on the penetration of the column. And this is giving that even if you are limited by your flexural resistance, you will punch. And this is what we see unless you have greater reinforcement and then it breaks during the plastic hinge So this is the resistance that we are having in this point. And then we can see it as the crossing between two curves. One, which is the failure criterion. This is what would be explaining or defining what is the capacity that we are having for that level of opening of the cracks. Another, which is the curve of the load rotation, which is the demand. So how much shear are we introducing for that level of rotation? And when they cross, when they intersect, then we have failure. And this happens not only when we are having yielding, but also we have this when we have more compact slabs, then we could have this punching when we are having some partial bending, yielding of the flexural reinforcement, or even no yielding at all. So this might be very brittle before any reinforcement yields, or when they are partially yielded, we can find a state of demand and capacity that match. And so we have a failure associated. So all these points here, they will define this failure region that we were describing here, this region of punching failure. They are more or less connected in this manner. So the higher, or let's say the lower the deformation, let's say psi as a parameter to measure that, the lower the deformation, the lower the opening of the cracks, the higher the capacity we can engage through the two surfaces. In the largest the cracks they open, the lowest the shear resisting actions will transfer shear. So now, once we know that, we can, by the way, we can integrate now and calculate what is the amount of resistance. So we have here what I was saying, this is a kinematical model. So it's one crack that is characterized by a shape, which is again like a parabola, and also with this point of distance, well, just a geometrical characterization. And then it has a rotation, which is giving this blue component of opening, and then a penetration. And by having this, you can go to constitutive lows. So from top to bottom, then you can say, okay, here in the delamination, as you know, Baumann-Rusch test, you can calculate that delamination is rather plastic, because once you start delaminating, it delaminates at a further distance. So you can calculate what is the contribution of double action. You can calculate within this crack, which is the largest part, what is the aggregate interlock. So opening and shearing, as you see, you can transfer perpendicular and tangential stresses or residual stresses. And also in the bottom part, which is very active, you get the compression, the response of concreting compression. This response, it depends on the state of lateral strength that we are having. So with the kinematics and some constitutive laws, it's simple. You can integrate all of them, and then you get the state of stresses. So you're getting a stress field which is based on the kinematics that we assume as some constitutive laws. And here you see, this is a calculation, by the way, where is the intensity, where the force is being transferred. So a large part is transferred on bottom, but also through the crack, through the crack, there is something which is being transferred. So this is the way the theory, the critical shear crack theory works. By the way, you can do this and solve this numerically. This is, for instance, instances of these numerical solutions for different cases, and you can see that when this is associated, its phi is associated to rotations. The larger the rotations, the cracks open more, you transfer less through aggregate interlock on top, and everything concentrates on bottom. However, when you have small levels of rotation, small levels of deformation, cracks are not that open, and then you can mobilize this transfer of shear stresses through larger regions. And this is consistent to what we were seeing before, that the lowest the deformation, the higher the resistance you could have. And this idea actually is, we would say, okay, and then this is a critical shear crack, and we may go. But this is, there's a sentence I like very much that says that doing a complex model is very simple, and doing a simple model is very complex. No? So here, this is what could be the complex model, which is not very simple to be done, but in fact, yes, it's just putting material parameters and getting it. This is the what would be the complex formulation. But I think a brilliant idea was to make a simple model from all this. So how we simplify all this something that we can use in a practical manner. And this idea is that was an original work by Professor Mutoni. By the way, that idea that was how could it be calculated? So these two parameter kinematical model, in fact, these two parameters, they are related, and this is a very good point, because if you try to imagine that you have a crack, for instance, in an aggregate, if your crack opens little, then you need little penetration to have contact again. If your crack opens a lot, then you need lots of penetration to have contact again. So both are related. So the largest the psi, the largest the delta. And in fact, if you calculate them, you see that it is not as I was doing with my hands, it's not linear, but actually both parameters, both kinematical parameters are related, namely for slender slabs. For compact footings and so on, it's not the case, then you need the two parameters. But for slender flat slabs, this is the case. So you can assume linearity between both, between time and delta, between the two parameters. And this allows you to calculate that the key parameter, which is the opening of the crack, this W, which is over here, is dependent eventually only on one parameter, which is, for instance, the rotation of the slab. And this is this assumption. So we assume that the opening of the crack width, W, so is proportional to psi times D. And then when you try to compare what results from literature they match against this assumption, you see that they closely follow this region band, and then you can describe on average with some uncertainty, of course, Mark, but you can describe with a simple failure criterion. This is, for instance, the hyperbolic failure criterion of the critical shear crack. And this is very, very simple. But please don't lose the key parameter actually is the crack width, is W. And I'm saying this going back to the presentation of Sarah. The test of Sarah, I spoke with her yesterday. Those were the tests that I wanted to do since many years ago. So Sarah was first. Congratulations. And that you were showing something to me very interesting that also was used as a contradiction to the critical crack theory, but it is exactly saying what the theory says, no? Because as you were showing in your long-term test, you were stating that the strength, the resistance was rather constant, while the rotations were increasing, the deflections were increasing. And this may seem contradictory because you will say, okay, but if psi increases, then the resistance shall decrease. No, not at all, because the parameter is not the rotation. Rotation is what is giving us an idea of what's happening. The parameter is the opening of the cracks. When you are having long-term, this is something with I thought that with a colleague of mine, Eduard Faria, many time ago, but we never had the test to demonstrate it. But our idea is that, in fact, in this you showed in your paper, the strain in the reinforcement is relatively constant. So it doesn't vary that much. There are some redistributions, but it doesn't vary that much. This means that if the strain here in the reinforcement is constant, what's happening is that the compression zone is actually creeping, and this is making the slab turning, but this is not increasing the opening of the cracks. You see, the crack width is a block on top, or increasing a little bit, but then the neutral axis is also raising. So the opening of the critical shear crack remains rather stable, even if the rotations are not the same. I'm sorry, because this is a point that I saw while reading Sarah's paper. I think it's a clear demonstration again that what works on what is the key parameter is this opening of the cracks, and it's very consistent with the theory. And also another advantage, because we have been focusing on this failure criterion, is what happens with the load rotation relationship. This is very, very interesting point also, because as the theory is mechanically consistent, so it's based on a model with all its limitations, of course, but you can refine the different parameters gradually, step by step. And then you may calculate this demand that we are having in the critical shear region by simplified assumption. For instance, we take a simplified parabola like this one. Well, it is derived on some configuration, several simplifications, but in fact, it is on the right proposal. This is very simple. So you have failure criterion defined by this simple equation and the load rotation demand defined by this equation. This is what you find for design, at least in the Swiss code and also in the model code for lower levels of approximation. So this is what you can do in a very simple manner. But solving this equation is not at all easy. No, it's not as easy. It's simply that it has no closed form solution. And so if you plug this psi here, you will not get any closed form solution. So you have to do it numerically if you want to solve it. You can design without solving numerically, just checking the strength. But if you want to solve it, you have to do it numerically. But something interesting is that this is giving you strength, but you could get a better estimate of what is the response of your member. For instance, you can use a more comprehensive model of the slab. And by assuming, for instance, a bilinear response, then you will get another estimate of how the slab behaves. And you see that from that on, when you refine, you get normally a benefit, you get higher strength because you are predicting a bit better what happens. And also you could also take a quadrilinear response, and then you could predict a bit better by considering tension stiffening effects and so on. And then you still keep on increasing what is the prediction of the strength. And this is what we call the levels of approximation approach, that you can start with very simple considerations and calculate in a simple manner, or you can refine and spend some hours and then get a better estimate. More than that, you can even refine in a larger manner. And again, as Sarah was showing with the full system, and you try also to extend a bit, and you can consider a compressive membrane action. You can consider redistribution between hogging and sagging bending moments. So everything you can put inside, and then you will get another curve, which is for the full flat slab, and then you can get high benefits. And what's the sake of this? It's not saying, okay, very intelligent researcher, and you are getting better results every time. It's not at all that. It's that for design, normally you can stick here, but when you are assessing an existing structure and it doesn't comply with the required resistance here, at least you have a tool where you can get a better prediction. You can get and say, okay, yes, perhaps with a design criterion or a typical design approach, it doesn't work, but when I assess it with a refined approach, consistent with the one for design, it works. And so it stands. I think it is a strategy which is, in my professional experience, helping to save lots of money. There are also considerations, but I will not go very much in detail, but as this parameter is, sorry, I don't have too much time, sorry, but as this parameter is depending also something I think is very interesting. It depends on the rotation, so on a strain parameter, and it depends also on a size parameter. So the actual key parameter, it depends on the strain and the size. And then you could have, by increasing the strain, you have this strain effect. By increasing the size, you also get a size effect. So more strain or more size decrease your strain. This is something you can calculate consistently. This is what you see in tests, actually. Is of larger size, they have lower strength, lower resistance. And then this is what you get also in the theory. So if now we normalize the rotation by the size of the member, then you can, for higher scales, you are moving in this direction. So you're getting lower resistance. For lower scales, you are moving in this direction. So you are moving up. And you will eventually find that there is a limit to what you can get in patching. And this without plugging any coefficient, without doing any trick, then you can express this in terms of double log scale, and then you get what is normally called not only the size effect factor, but the full size effect law, as described, for instance, by Dajan. And so, depending upon your considerations, it may vary a bit. So, for instance, for the parabola, what you're getting is that you're having this decay. It is going up to a limit, which is the strength criterion. This point here cannot be higher than this point. But when you have larger sizes, it decreases. It decreases about a slope 1 to 3. This is basically. Interestingly, when you're getting this relation, which is the linear, when we were saying the bilinear law, and if you are failing within the linear part of the response, you're getting a slope of 1/2. 1/2, if you know, as you may typically know, is the slope that linear elastic fracture mechanics gives you. And this is because this is linear elastic. So if you assume a linear elastic response of the member, you will get the slope of linear elastic fracture mechanics. While these slopes, which are milder, they are associated to some level of nonlinearity. All these cracks and this plasticity, even regions that are yielding and so on, and tension stiffening effects and so on. So it's a very consistent theory, and I was stating you can use it in different levels. No? So for design, we are typically using the hyperbolic failure criterion and the parabola, and then what model for 2020 is advising you to use, which is called level of approximation 2 or 3, depending upon that you define the parameters with some geometric ratios or some mechanical ratios. Then, as you have to get the resistance, you have to solve iteratively. Not for design, but for assessment, you need to do that. In the next generation of Eurocode, there was a change in the hyperbolic failure criterion, changing it to a power law, and then you can calculate in a closed form manner what is the expression that you will get with the theory, and this is the equation that you will see in the code, which is not that far to what was before, but now it is derived from a theory, and that allows using in a very compact manner. And by the way, you see that here is D, and this is the power 1/3. So this is the size effect factor, if you want. And for assessment, it is opening the door to much more complex analysis. For instance, this full flat slab with redistribution between holding and sagging regions and so on. And this is acquired in model code, for instance, model code level 4, but also in Annex I, which is informative, by the way, of the EREN, so the future Eurocode as it is now. Now that the theory was explained, sorry for that, we can go to what are the changes that we need to do, or what are the considerations that we need to do for assessing these extreme events. So I think there's an animation here. I don't know if you can. This is the test done by Alejandro Perez at UPM. It's not a test of mine. And it's interesting, it was this flat slab, and then they removed this column. You will see what happens. They remove the column, and it doesn't fall. But to me, the important thing is not that it doesn't fall, it's the speed that was of the test. So I think also in the video of Sarah was a bit similar. It is not something that happens in a 10th or 100th of fraction of second. I think you can put it again, but it is something that happens in the scale of 1 second. This is at least my perception. And you will see again, but this is also what measurements they give. We're working at the scales that are of the order of the second. And this is, you will see, now it will be removed. And this is something that happens, but it's not an explosion. It's not at the rates of Mark. It's a different pace. And this is extremely important for me. And because the question that we are having is now, if we remove a column, what's happening in the load rotation relationship and what's happening in the failure criterion? This is a work also when Francis Rosetta worked intensively some time ago, and he obtained very, very clear answers to that. So with respect to the failure criterion, unless you go to very high strain rates, it's almost unchanged. So for the scale of column removal, we can keep the same failure criterion as for the critical shear crack theory under static considerations. And what happens with the load rotation relationship? Well, basically the same. Again, if you characterize the load rotation relationship, you need to have so that the changes in the modulus of elasticity and the fractal properties, they start having a real influence. You will see basically the same. And why is it relevant? Because if you were, and this is the good point, if you could place here, somewhere here, and this is why I'm putting here, a load cell, and you were measuring what was the force that was in the column with respect to the level of rotation, this will work perfectly. But if you place your load cell here, the issue is that the load cell here at the column will not be providing you the value of the gravity loads that you're having. Because here, even if it is a scale of a second, you have inertial loads. You have an increase of the load. And this is the important point. So this is, for instance, some numerical simulations. These are not mine. These were done by Juan. Where he was testing with a linear finite element on the potential, what was their response after these extreme events. And he was seeing that it was following closely the static curve that we could predict, and it was failing about in the failure criterion of the critical shear crack theory. So everything is correct, but the level of gravity load which is associated is lower. This is the level of gravity load. So your structure, if you want to calculate how much static kilonewtons you had here, you would be somewhere here, but the connection is seeing a higher level of demand. This is the real difference which is happening. But the characterization of the response in terms of load rotation and in terms of resistance, they are basically the same. So now, of course, all the discussion happens in this, and I want to show also some that just to show that this is really what's happening, or I feel that this is really what's happening. We did some tests in Lausanne that they were very similar to the test of Sarah, but in one-way shear. So these were beams in shear, not slabs in punching, where we were loading these beams until up to failure, varying between 1 second and some weeks. But it was interesting because when we can't, to be honest, we couldn't load faster because you are not capable of putting so much load in the hydraulic jacks less than 1 second. At least we were not capable. That's the limit that we could be using experimentally. But it was good because it was basically what we see in column removal cases. And what we saw is that the strength was rather constant. There were some, perhaps a bit of decrease, but even you may say, yes, but for 1 second it raises, Miguel. No, it raises, but not necessarily. There was a first failure, and then it dropped, and then we were capable of reloading it. And in fact, it was not, you see, the first failure was about the same. And I was going to say, okay, so are the materials changing so dramatically that you almost see something or what's happening? No, in fact, not at all. That was a very interesting conclusion for me, that the change that may explain why this is a bit higher or there are reductions is not in the material itself. The difference is in the shape of the cracks. And then you see it here. This is a very fast loading, and this is the shape of the critical crack, which is that one. And as you see, it is very low. While when we are doing long-term loading or long-term loading, but even some days or some hours, what you see is that the critical shear crack is not that one. The critical shear crack is starting far away, and it's rather consistent. So the critical shear crack is shifting. And so while here you could, after first crack, you could still have a direct strat, then you cannot have it in the other cases. So what was changing, in fact, was not the material properties. The changes in the strength that were observed were basically due to the difference in the shape of the crack, in the kinematics of the crack. But we saw very consistent results to Sarah, by the way, because we were not capable of breaking any in long term any of the beams that we had, and so we needed to reload them, as you were doing also, in order to reach failure. And we saw, I think also consistently to what you were saying, that failure was in fact triggered in some seconds at the very end. So it doesn't matter what was happening here, almost nothing. It was just the very end minutes that everything was triggered and leading to failure. So seeing that and saying that it's sound validation of what we are doing. Now, the idea, the work that we are doing, where Juan and Maria are doing, and I'm implied, is to characterize these curves, and particularly not in determining equations. This already they were developed by Juan, but also how can we frame all this within a closed form solution? So we want, if that's the expression that I was showing for the TREN, so for the future draft of Eurocode, how can we turn this expression into something closed form that allows a designer to know what would be the level of static load that would be capable of managing this structure under punching for an extreme event. And this would be a major breakthrough because you can't keep doing complex nonlinear finite elements just to get this answer, but you could do very simple checks, even closed form checks at every connection. This would be, I think, a very good contribution. And as I'm creating here, Maria Lapopolo, which is doing an excellent work from my point of view and Juan's point of view, very, very good progress on this. And finally, and going back to reliability, some of the questions that we would like to address, but we don't have a research timing very precise, but I think sooner or later we would have also to give an answer to what is the level of reliability that we have to adopt. So, in particularly in what is the difference here, we have an extreme event, and it's very difficult to determine what is the probability of occurrence of the hazard. This is the key point, and this is very difficult that we are capable of giving an answer. So this is the first point. So these are consequent classes, and in how do we characterize the let's say not the cost of construction, but the risk curve, no? So the sum of all the cost after failure, and how to change this to an existing structure. This has been lots of work for in seismic field, because we cannot start now strengthening every single structure that exists. We need to do something more clever. We have to understand what is the level of investment that we can accept as a society to strengthen our structure so that we find what is the optimum cost for the society. So we cannot strengthen as if they were new structures, but we have to do something because also what Enduri is giving now would be extremely sound and rules for next generation of buildings. But in any case, this will be a part of the buildings. But the day after, we will have a massive amount of buildings that we will not know what to do with, and it would be useless to start strengthening for design values of reliability. So we will need to find what is the right target that we could claim engineers and designers to assess. Okay, so I think that was everything from my presentation, which I probably exceeded. Okay, okay.
Miguel, thanks for your nice presentation. We have time for some questions because we have a kind of structural views regarding the schedule today. Okay, so we have some time. Mark Stewart?
Yeah, that was a lovely talk. Yeah. I like a comment at the end about existing structures because that's the real challenge.
Yes.
You know, so are you doing any research to try to think about what's the acceptable level of cost and safety?
Exactly.
And how to apply that going forward?
Exactly. Well, we have until now we have done not for extreme events. We have done for let's say maintenance issues, basically, where we calculate is what is the current level of reliability, and then we have a limit value, beta limit, which is here, which is the social acceptance to that, which is about 3, basically more or less about 3. There are huge discussions, but it's about 3 normally. And then if these were the 3.8 or 4.2, whatever, if you, well, I'm speaking in 50 years, reference period, then you do not need to strengthen for a 3.8. And where do you need to stop? And normally, where do you need to stop? Larger than 3. This is, or let's say, this is, well, we have done some analysis, and it's true that it's very, normally it depends on the process that you're having. If you have mass corrosion, for instance, or timber and it's everything almost destroyed by humidity, then it's better that even you demolish the building. But if you have, for instance, is problems due to punching, which is very localized, because punching of all this, you only need to strengthen a small region close to the column, then it is very efficient intervention. And then you can, with a small investment, you can reduce the risk of the owner so much that it becomes interesting. And so this is the investigation. And there was a figure here, C, which is not, because sometimes this is the scenario where the investment is larger than the reduction in the risk. And then you say, once you get to the beta zero limit, you destroy and you change and this is where the investment is good. And they were here and there, but it was not coming to the point. But normally maintenance is a good strategy, because with maintenance you can change the beta with very small investment in time. You can turn the beta to be the acceptable value for a new structure. This is what we are trying to encourage. But how to frame this, how to calculate the risk curve in case of extreme events is the big challenge, because what 10 to the powers what till so what's the probability of occurrence of a hazard? This is very, very difficult, actually. It's even something you have to discuss with your owner. Very, I don't have an answer at this. Yeah. Yeah.
Thank you very much. More questions? Carlos Lázaro? Thank you for the very interesting lecture. And I have a question about the model. The model seems to rely on an assumption on the geometry of the crack. And I think you addressed it at the end of your explanation. So how sensitive is the model to different crack geometries?
Yes, not that much, actually, not that much. So you could take almost a linear crack, and what is changing quite a lot is the angle that it's having. In this angle, this is relatively well characterized because it depends a lot on the amount of flexural reinforcement. So, so when you're having a lower reinforcement, it is more vertical. When you're having larger reinforcement, it is more horizontal. And this is the controlling parameter. But in any case, in the end, in Carlos, we forget about what is the shape. So this is only something we do as a mental construction just to it. But in the end, here, this expression was even done before this analysis was before the analysis were done. So it was just seeing that all the experiments, they were working in a similar manner. And if you produce something that changes the shape of the crack, I don't know, difference in bond conditions or discontinuity or something, then this curve may change. And then you need to go to the let's say to the basic theory model and redo the work. But not that sensitive, I would say, in any case. And you see here, you have many cases, different reinforcement ratios, different sizes, and you get some scatter, obviously, because there are changes in this shape, but they are still acceptable. Yeah. Thanks. Thank you.
So, Miguel, thank you very much for your very interesting presentation.
Okay. Thank you.
So it's time for our last talk by Dr. Nirvan Makoond. Nirvan is a postdoctoral researcher here at the UPV working on structural robustness, risk assessment, reliability, and also computational modeling. The title of his talk is Full-Scale Testing of a Precast Building. This is an experimental campaign we perform within the framework of Endure, our European project. So, Nirvan, the floor is yours. Ready?
Okay. All right. Well, hello everyone. So, my name is Nirvan, as I said, and I'll present to you the test we performed last year to evaluate the effectiveness and viability of fuse-based testing for a precast concrete building. So I've structured my talk in 6 sections, more or less. So I'll start by giving just a very brief review of the point mentioned by Andri on what is fuse-based segmentation before moving on to the building design and the simulations we performed to plan our experimental campaign. I will then describe a bit the building construction, the planning of the test, and the test setup, before addressing the main results of the test, specifically aspects pertaining to avoiding the initiation of collapse and arresting collapse propagation before summarizing the main conclusions. So as Andri mentioned, so basically the main idea behind fuse-based segmentation is it's a design approach which involves basically ensuring continuity for operational conditions or small initial failures. But when large initial failures occurs for which collapse initiation is inevitable, the approach in itself ensures that the collapse is arrested by controlling the hierarchy of failures, basically, that occurs. And the lizard analogy is a very good one for the approach, in my opinion. So the concept of fuse-based segmentation makes an important distinction between two types of initial failures. So small initial failures for which it is possible to prevent collapse initiation through load redistribution, and large initial failures for which collapse initiation is inevitable. So from now on, I will always refer to these as either small initial failures or large initial failures, but these are basically the definitions for these two types of failures, which are not universal. So to investigate and test the applicability of this design approach in a real building, we devised a design problem. So we chose a precast building because it's being increasingly used for high occupancy buildings in this part of the world, for malls and hospitals, for instance. And the building specimen has basically consists of a 12 by 15 meter building with two floors of 2.6 meters. So this represents a building which could be feasibly tested at full scale, while also basically employing construction techniques which are still common and useful for industry. So in our investigation, basically we looked at two different design options. So the first one involved the fuse-based segmented design, which through specifically designed connections and enhanced columns, basically we ensured that during a collapse process at the boundary of a moving collapse, the failure would always occur in at the connection or in part of the floor system before successive column failures occurs. And in the opposite case, our base case for comparison basically was a conventional design, which was designed more strictly according to codes with full strength connections to maximize continuity, basically. So the first design, we labeled it design A, basically for because we control the hierarchy of failures, so for hierarchy-based collapse isolation, and design C for the conventional design. Here I've shown again basically some of the details of the partial strength connections which allowed this to happen. So as we can see, both design H and design C basically had three continuity bars going through the prepared sleeves in the precast columns. And in the case of design H, the dowel bars were designed specifically so that basically failure would happen before of the column reinforcement. And okay, so we performed some simulations for basically fine tuning the designs, and here we see basically the result after an extreme small initial failure. So one for which load redistribution could still avoid the initiation of collapse. And left I've shown basically the principal normal strains in the case of the fuse-based segmented design, and to the right, the conventional design. As we could expect, so the fuse-based segmentation design is slightly more strained for this case, whereas the conventional design with more continuity is less strained for this situation because it distributes the load better. However, after large initial failures and after a large initial failure involving basically the removal of this the three edge columns supporting this corner bay, and here we have the fuse-based segmentation design, which basically only results in partial collapse, whereas the conventional design basically leads to total collapse in this case. So here I've shown some details about the interior column, which is just adjacent to this corner bay for which the three supporting columns were removed. And I've shown the evolution of actual loads, bending moments, and shear forces in this column and compared them for the two cases. And basically, this I've also so the evolution of the loads in comparison to the capacity curves, minimum and maximum capacity based on the actual forces, on the level of actual forces there. And as we can see here, this explains basically the failure that then triggered the rest of the collapse propagation. And okay, so this basically these initial results gave us an indication that fuse-based segmentation could be valid for this type of structure, and it allowed us. And with these results, we then proceeded to the building construction. So here I've shown some of the details I mentioned previously. So the dowel bars, and the building consisted basically of precast columns, partially precast beams that were placed on top of the core bells of the columns, and the columns were prepared with sleeves through which the continuity bars were placed. And here we can see the column prior to placing the precast part of the beam, and here after the precast part, after the beams were positioned. And okay, so here this is showing the construction process. So first, the foundations were laid, the precast columns were erected, and the precast part of the beams were positioned on top of them. Then the hollow core planks were positioned over the beams, and finally the topping was poured on top, which completed the hollow core slab, and also completed the slab, and also the cast in place portion of the beam. Okay, so so then we evaluated different initial failure scenarios to decide basically the final testing scenario we would evaluate. And so we evaluated three different scenarios. Basically, we considered three different scenarios. The first one consists of two columns to the in this part of the columns, and basically it would cause segmentation along a single line of failure, so unidirectional segmentation. And the third one, which was the one we finally chose, basically involved the removal of these three columns and a corner bay. So we chose it one because it gave us the best margins with respect to the amount of load needed for collapse and the amount of to initiate the collapse, and also the safety while loading the structure. But also from the scientific point of view, it was more interesting to have failure along two planes to really test how well the segmentation approach was working. Also, our approach we were able to test it at least theoretically very well based on the connection of the beams and the columns. But we did always have some slight uncertainty based on the topping reinforcement in the other direction as to how that would behave. So we were keen to test it. And okay, so this here I've just summarized a bit how we executed how we plan to execute the test. So we The test was to be executed in two phases. In a first phase, we plan to remove quasi-statically the first, so two penultimate columns using this test that was prepared, and involving a hydraulic jack that could be gradually lowered. And the second phase of testing would involve dynamically removing the corner column. So and we used about 8,000 pounds to impose a load of 11.8 kilonewtons. So the magnitude of the load, we also decided on it because the first phase of testing was to be quasi-static, and to ensure that the alternative load paths would also were also valid for a dynamic removal. We basically magnified the load by significantly, and at the same time, we knew that this load would also ensure collapse could be initiated in the second phase based on our previous simulation results. And we loaded the structure only partially, because, well, we performed several simulations to compare basically what we could expect the difference to be between partial loading and fully loading the structure. Expected to be quite similar. However, in the case of partial loading, basically the drifts in the part of the structure we expected to remain upright were larger, and therefore, and there was a greater balance moment being transferred to that part of the structure because it didn't have any. The columns had less, basically had a lower level of compression also. So in that, therefore, this case was more critical for the upright part of the structure, and therefore it was of interest for us to test basically and that it could resist the pulling forces as we expected. Okay, so for the test, we monitored extensively the structure, also to calibrate our results, but also to calibrate our simulations, but especially to better understand how the segmentation was occurring along the segment borders, and to verify the damage in the intact part of the structure. So we used 57 embedded strain gauges that were connected at that point in different parts of the structure, displacement transducers to measure horizontal displacement, and accelerometers. Okay, so this video, basically we will see the first phase of testing, which involved the quasi-static removal of this column and this column gradually, and then basically the apparatus was pulled out to prepare for the second phase of testing. So the first, so here we will see what one of the first columns has already been removed and the apparatus lowered. Now the hydraulic jack is being lowered from a distance, and this has already been pulled out. And as we can see, there's actually fairly small deflections. At this stage, the load was redistributed quite efficiently through the beams, columns, and slabs. And here we summarize the results. So as we can see, the displacement was very small, still significantly lower than the depth of the beam, so not sufficient to activate catenary action, even with such a high magnitude of loading. There was fairly limited damage to reinforcement, with just some of the reinforcement of the continuity reinforcement in the top beams yielding, just about yielding. And here I've basically shown the redistribution of loads to the adjacent columns, which allowed us to see a bit how the alternative load paths were developed experimentally. Okay, for the second phase of testing, we used the specifically designed collapsible column. Here we can see it in its fully collapsed form. So we designed it so that it could go maximum possible. And yeah, so that the three hinge could descend as much as possible. And in prior to testing the second phase, basically this middle hinge was locked, and it was unlocked from a distance, and then given a slight destabilization to activate the sudden removal of the column, which is what we can see in this video here, just showing the second phase, which is the collapse part of the structure. As we can see, so the failure of the partial strength connections occurred, and the rupture of the continuity bars and that connection occurred prior to any failure of columns, and also the basically the creating a segment border between the columns just outside the influence area of this initial failure. And here, basically, these are some of the interesting results we were able to collect. So as we can see, only the influence area of the initial part collapsed, and basically here the connections failed, and along all the slab there was debonding of the reinforcement. So this here in these plots I'm showing the change in the axial strain for column C7 and drifts measured basically in this part of the structure, so in the intact part of the structure. So as in the initial phases, as the column C12 was removed, just after the sudden removal, basically the whole structure was moving basically in this direction, so southwest in this case, according to this compass. And basically there was it kept on moving in that direction, but shortly after the failure of the connection around C7, basically there is a backward recoil, and basically this shows basically a tugging effect, which then the movement of the remaining part of the structure went into a attenuating oscillatory motion until it stabilized with a relatively with a notable residual drift. So this gives us an indication that basically the horizontal forces were quite significant, and the peak drift could be compared to the maximum allowable when designing for an earthquake of 2,500 year return period, which shows that it's quite significant. The residual drift and also the dynamic nature of this motion, as well as measurements of yielded reinforcement in the part of the structure, especially close to the segment border, indicate to us that it did suffer notable damage. However, it was still sufficiently safe for it will still be sufficiently safe for safe evacuation and rescue operations. And in fact, we visited it even a year after, and it's still intact, more or less, the structure. And here I would like just to show, basically, we can see a closer view of segment border, but also the rupture along the connection, and basically the debonding the in the slab, which the debonding in the slab, which basically enabled the segmentation to happen quite smoothly in this area. So here we can see the debonded rebars in the slab, and the rupture, for example, the rupture of the continuity bars here, and the failure and cracking of the core bells, which happened at the connections. And Okay, so here I so the simulations we performed basically to plan out tests also turned out to predict very well the the actual the actual observed structural response, and the assumptions we had to make were reasonable, all based on quite basically theoretical assumptions we could make before. And okay, so this brings me to the conclusion. So the test showed that the design complies with robustness requirements in building codes. We could see that in phase 1 of testing. Labs could be arrested after a large initial failure, which is what we saw in phase 2. We also showed that more conventional robustness design would have led to total collapse for the same large initial failure. There was some damage suffered in the upright building segment, but safe evacuation and rescue would still be possible. Yeah, I acknowledge the funding for the project and our partners, the League Construction Company and Applied Science International. And thank you very much for your attention.
Thanks, Nirvan, for your talk and also for participating in the project and the experimental campaign. So I have to say that Nirvan performed the computational simulation before the test, and before the test, we published these models on social media. So we put another risk for the day of the test. So we wanted to comply with the experimental campaign, what we predicted with the computational model. And in the end, everything was okay. So it's time for questions because this is our last presentation. Couple of questions for Nirvan or for the project. Mark Stewart, please.
Thanks, Simon. That's really exciting piece of research. I've never seen so many great videos. Those would be great. Now, with me, I always like to think about what's the variability of the material properties. So, did you do lots of tests to characterize particularly the compressive strength and the yield strength and all those other aspects of the materials?
Yeah, so we collected a lot of core specimens on the concrete. We did a test on the rebars to characterize the ultimate strength, the yield strength, the ultimate strain, and basically we used mean values for our simulation. So we didn't. We did some sensitivity studies. I wouldn't say we did a full reliability analysis before. We did some sensitivity studies and we employed mean value for our predictive simulations.
That's the best answer I was hoping for. Thanks.
So, any questions? More questions? So that's all. I think that is the end of the workshop. I want to thank you all for coming, for your participation, especially to our speakers, Andri Setiawan, Mark Stewart, Sarah Orton, thank you very much. Renata Obiala, thank you very much. Miguel Fernádez and Nirvan. So thank you very much to all. Yeah.